Hi, my name is James Church, and this is Beginning Haskell Data Analysis from Packt Publishing. In this course, we are going to learn about data analysis from the perspective of the Haskell programming language. We are going to use the IHaskell environment on the Jupyter Notebook system. Now, a little bit about myself. For the past several years, I have been a professor of higher education and I have been a consultant for several companies, as well as the United States National Institute on Drug Abuse. Finally, I am the author of Learning Haskell Data Analysis, also by Packt Publishers. In section 1 of this course, we are going to cover the CSV file format, as well as descriptive statistics. Now, the descriptive statistics we're going to cover are going to be the ones that you're most familiar with, the mean and the mode and the standard deviation. In section 2 of this course, we're going to cover the SQLite 3 database, which is a popular database engine for working with flat files. In the third section of this course, we're going to be working with regular expressions. Regular expressions are a textual pattern that allows us to filter data, and it allows us to make sure that columns in our data match a particular standard. In section 4 of this course, we are going to create compelling visualizations and make publication-ready charts and graphs. In section 5 of this course, we are going to learn about the normal distribution. And using that normal distribution, we are going to create a visualization known as the kernel density estimator. In section 6 of this course, we are going to wrap it all up with a start-to-finish example using the movie lens dataset, where we tie together the first 5 sections. The goal for this course is to take you from a beginner in math and statistics and get you comfortable working with large-scale datasets. Now, the prerequisites for this course are that you know a little bit of the Haskell programming language. You also know a little bit of math and statistics. From there, we can start you on the journey of becoming a data analyst. Well, here we go.
Welcome to Descriptive Statistics. Descriptive statistics are used to summarize a collection of values into 1 or 2 values. We begin with learning about the Haskell text.csv library. In future videos, we will cover, in increasing difficulty, the range, mean, median, and the mode. And you've probably heard of some of these descriptive statistics before. They're quite common. So in this video, we're going to cover the basics of the CSV library and how to work with CSV files. So in this video, we're going to take a closer look at the structure of a CSV file, how to install the text.csv Haskell library, and how to retrieve data from a CSV file from within Haskell. Now, to begin, we need a CSV file. So I'm going to tab over to my Haskell environment, which is just a Debian Linux virtual machine running on my computer. And I'm going to go to the website retrosheet.org. Retrosheet.org is a website for baseball statistics, and I'm going to use them to demonstrate the CSV library. Now, if we find the link for data downloads and click Game Logs and scroll down just a little bit, we have game logs for every single season going all the way back to 1871. For now, I would like to stick with the most recent complete season, which is 2015. So go ahead and click that link. We will have the ability to download a zip file, so go ahead and click OK. And I'm going to tab over to my terminal. And let's go into the Downloads folder. And if I hit LS, I see that there's our zip file. Let's unzip that file and see what we have. Let's open up gl2015.txt. This is a CSV file. A CSV file is a file of comma-separated values. So you'll see that we have a file divided up where each line in this file is a record, and each record represents a single game of baseball in the 2015 season. And every single record is a listing of values separated by a comma. So the very first game in this data set is a game between the St. Louis Cardinals, that's the SLN, and the Chicago Cubs, that's the CHN. And this game took place on March 5th, 2015. The final score of this game was 3-0. And every line in this file is a different game. So I'm going to scroll down and just demonstrate that we have many, many games represented in this file, and lots of information that we could look at. So I'm back up at the top of the file. Now CSV isn't a standard, but there are a few properties of a CSV file which I consider to be safe. Consider these my suggestions. Now a CSV file should keep one record per line. The first line should be a description of each column. In a future video, I'm going to tell you that we need to remove this header line, and you'll see that this particular file doesn't have this header line. I still like to see the description line for each column of values. If a field in a record includes a comma, then that field should be surrounded by quote marks. Now we don't see an example of this, at least on this first line, but we do see examples of many values having quote marks surrounding the file, such as the very first value, the date. In a CSV file, if a field is surrounded by quote marks, that is optional unless it has a comma inside that value. While we're here, I would like to make a note of the 10th column in this file, and that contains the number 3 on this particular row. That represents the away team's score in every single record of this file. Make a note that our first value on the 10th column is a 3. We're going to come back to that later on. Let me get out of my file. Our next task is installing the text.csv library, and we do that using the Cabal tool, which connects with the Hackage repository and downloads the text.csv library. The command for that is cabal install csv. It takes a moment to download the file, but it's going to download and install the text.csv library in our home folder. Now let me describe what I have currently in my home folder. I like to create a directory for my code called code, and inside here I have a directory called Haskell Data Analysis. And inside Haskell Data Analysis I have two directories called Analysis and Data. In the Analysis folder I would like to store my notebooks. In the Data folder I would like to store my datasets. That way I can keep a distinction between analysis files and data files. That means I need to move my data file that I just downloaded into my data folder. So copy from our downloads folder our gl2015.txt into our data folder. If I do an ls on my data folder, I'll see that I've got my file. I'm going to go into my analysis folder, which currently contains nothing, and I'm going to start the Jupyter notebook. Now Jupyter is spelled Jupyter. And what the Jupyter notebook does is it starts a web server on your computer, and it uses your web browser in order to interact with Haskell. And the address for the Jupyter notebook is localhost at port 8888. Now I'm going to create a new Haskell notebook. I click over here on the new command on the right side of the screen, and I find Haskell. Let's begin by renaming our notebook Baseball, because we're going to be looking at baseball statistics. I need to import that text.csv file that we just installed. In order to submit an expression to the Jupyter environment, we need to hit Shift-Enter on the keyboard. Now, if you're just in a box and you hit Enter, you're just making that text field larger. You hit Shift-Enter in order to submit expressions. So now that we've imported text.csv, let's create our baseball dataset and parse the dataset. So the command for that is parse csv from file, and then we pass in the location of our text file. Great. And if you didn't get a file not found error at this point, that means you have successfully parsed the data from the CSV file. Let's explore the type of baseball data. So to do that, we hit Type and Baseball, which is what we just created. And we see that we have either a parsing error or a CSV file. Now, I've already done this, so I know that there aren't any parsing errors in our CSV file. But if there are, they would be represented by parse error. So I can promise you, if you've gotten this far, I know that we have a working CSV file. Now, I'll be honest, I don't know why the CSV library does this, but the last element in every CSV data is a single empty list. And I call this empty list the empty row. What I would like to do is to create a quick function called noEmptyRows that removes any row of data that doesn't have at least two pieces of information in it. So either, and if we have a parsing error, we're just going to return back an empty list, or if we actually have data, we're going to filter out any row that does not have at least two pieces of information in that row. Now let's apply our noEmptyRows to our baseball dataset. I'm going to call this baseball list. Now we can do a quick check to see the length of the baseball list. And we should have 2,429 rows, representing 2,429 games played in the 2015 season. Now let's look at the type of baseball list. And we see that we have a list of fields. Now you may be asking yourself, what's a field? Now we can explore field using info. And it's going to bring up a window from the bottom of the screen. And I'm going to scroll this up a little bit, and it says type field is equal to string, and it's defined in the text.csv library. So just remember that a field is just a string. I'm going to close that. Now, because every value is a field, which is a string, if I do math on strings, that's going to produce an error message. So what I need to do is I need to parse that information from a string to something which I can use, such as an int or a double. And I do that with the read command. So if I say read1, I can parse that as an integer. Or I can say read 1.5, and I can parse that as a double. So armed with this knowledge of parsing data from strings, we can parse a column of data. So I would like to create a function, and we're going to call this function readIndex. And I'm going to say that each value is a cell in our case. So for each cell in our data set, we're going to pass in our original baseball data set. That is an either. And we're going to say that we need an int index position into our list, and we are going to return a list of cells. This requires two arguments, the CSV and the index position that we need. And we are going to map over each record, and we're going to read whatever exists at the specified index position. We also need the noEmptyRows that we discussed earlier. Good. Now if you recall earlier, I said that the away team scores in our CSV file exist on column 10. And because Haskell is a zero-based index file, that means we need to pass in index 9 to our readIndex function. So readIndex baseball 9. And we're going to parse this list that's returned as a list of integers. And there we have a listing of every single away team score in Major League Baseball. And the very first element in our list is a 3, because that is the first record of the file. So in this video, you learned about the structure of a CSV file. You learned how to install the text.csv library, and you learned how to pull a little bit of information out of that CSV file using the CSV library. So in our next video, we're going to discuss how to create our own module for descriptive statistics and how to write a function for the range of a data set. We begin with the data range descriptive statistic. This will be the easiest descriptive statistics that we cover in section 1. All it is grabbing the maximum and minimum of a set of values. So in this video, we're going to be taking a look at using the maximum and minimum functions in order to find the range of a data set. And we're going to be combining those functions into a single function, which returns a tuple of values. And finally, we're going to compute the range of our away team runs using the function that we prototyped. Let me find my Haskell notebooks in the Jupyter system. So when we last left our video, we pulled a listing of all the away team scores for each game in the 2015 season of Major League Baseball. If you're rejoining this video series after a break, you may have to find the kernel and restart run all feature. inside the notebook system. And I'm just going to do that to make sure that we get things going. Now, we do get a warning message saying that this will clear all of our variables, and that's okay because all of the variables are going to be rebuilt by the notebook. This menu option appeared. We're going to close that down. So this was the last thing that we did in our notebook from the last video. And what I would like to do is to store this in a variable called awayRuns. Now, in order to find the range of this data set, we're going to utilize two functions. And those two functions are maximum awayRuns. We see that the maximum number of runs scored by any away team in the 2015 season was 21. And we see that the minimum was 0. 21 sounds like a lot of runs. Let's take a moment and examine the type signatures of the maximum and minimum functions. They both take a list of values and return a single value, and the values are bound by the ORD type. With that knowledge, we're going to create a function called range that takes a value and returns a tuple of values bound by the ORD type. Let's go. So our quick function should probably look like this. So we're going to call this a range. We're going to be bounding our values by the ORD type. We're going to accept a range of values and return our tuple of values. And so we can just say range XS, and that will equal minimum XS maximum XS. Good. Now let's test this function. Alright, so range awayRuns. And we see that we get a range of 0 to 21. Now what if we pass an empty list? Or what if we just pass a list of one value? These are some things that we didn't consider in this function that I just wrote. So let's explore that for a little bit. So range and then an empty list. We see that we get an error message, prelude minimum empty list. And that's because our data was passed to the minimum function. It saw that we had an empty list and it threw an error. What we really ought to do is to package our return in a maybe so that we could potentially return nothing and adjust in case that we have empty list. So what I would like to do is to find my pre-written range code. I'm just going to copy this. And I'm going to paste this into the window. So this is our improved range function, and we use a little bit of pattern matching in order to adjust to some of the conditions that we should be looking for in a proper range function. So I still have a list of values that are bound by the ORD type, but now I am packaging my return inside of a maybe. That way I can adjust to circumstances in which an empty list is passed, such as returning nothing. If I have a single value, I can just return that value twice and not even have to worry with the minimum and maximum. But if I get anything else, I can utilize our minimum and maximum functions. That way I can type in range in an empty list, range 1, and range awayRuns. Great. So this improved function is going to be our prototyped goal for the remaining descriptive statistics in our video series. We're going to be adjusting accordingly based on the inputs given and returning none in cases where no results should be given. In our next video, we're going to be discussing how to compute the mean of a data set. Our next descriptive statistic covered will be the mean, also called the average, and the standard deviation. In this video, we will use the sum and length functions to compose the mean of a data set, and we'll explore the sum and length functions, compose our mean function, and then we will use that mean function in order to compose a standard deviation function. Finally, we're going to compute the mean and standard deviation of the 2015 away team runs using our function. The mean is a summary statistic which gives you a quick idea of the middle, while not truly being the middle, of a data set. The mean is trivial to calculate, and thus it is frequently used. And all it is the sum of that data set divided by the number of values in that data set. We also discussed sample standard deviation, which is the mean distance from the mean and a measure of a data set spread. The approach that we will be using is known as the sample standard deviation. I have the function presented here for your reference. Let's go over to our Linux environment, and here's where we left off discussing the range of a dataset. I would like to scroll up to the very top of our notebook and add a new import. And the import which I would like to add is import data.maybe. Now, because I have added a library, what I like to do each time I add libraries is to do a restart and rerun all. And it's okay to do this. We'll take a moment and it will reload all of our variables. Close that down. In order to compute the mean of a dataset, we add up all the values and divide it by the length of those values. So in order to find the sum of all the values in a list, we use sum away run. There were 10,091 runs scored in the 2015 season by away teams. We also need to know the length of the away runs. There were 2,429 games. We divide the first number by the second and we get our average. But we need to explore the type of the sum and the length functions. We can see that the sum takes a list of values and returns a value, and the inputs and the outputs are bound by the num type. Whereas the inputs on length aren't bound by anything, and they always return an int. Now, the division operator in Haskell doesn't work with int. So what we need to do is we need to convert the values returned by sum and length to something that we can work with. And so the function that we will be using is real to frac sum away runs divided by from integral length away runs. So our average is at 4.15 runs per game were scored by away teams in the 2015 season. We use this information in order to compose our mean function. And I already have it pasted here. Let's paste that. Much like our range function, we have a return type of a double that's been packaged into a maybe. And we have a list of values that are bound on the real type. Now, our function uses pattern matching in order to handle the variety of inputs and outputs that we will likely receive, much like we did with the range function in the last video. So if we have a list of no values, we return nothing. Now, it's best that we return nothing and not 0, because 0 could be interpreted as a mean of a dataset. If we have a single value, well, then we're just going to return that value bundled in a just. And if we have a list, well, then we're actually going to implement our sum and length functions that we described earlier. So let's test this out. If we get mean of an empty list, we should get nothing. If we get mean of a single value, we should get that value converted to a double. And if we have mean of a true list, we should get our average. Now, any function which uses our mean function is going to have to interpret the value inside of a maybe. And so in order to do that, we use a function called fromJust. I am now going to find my pre-written code for the standard deviation. I do this because it's easier just to copy and paste this code than to type it up. I'm going to paste this here, and we're going to talk about the standard deviation code. Much like the mean function which we wrote earlier, we have our inputs bound by a real type, and we will be returning a double packaged in a maybe. And for historic reasons, I call this function stdev. So statistical spreadsheet software and statistical packages will call this particular function stdev. And this is a recreation of the formula which I showed you in the beginning of this video, which produces the sample standard deviation. It's important to note that the sample standard deviation requires at least 2 values in order to compute a spread. You can't very well compute a spread with 1 value, and so we need to use pattern matching in order to detect that. So if we have an empty list, we return nothing. If we have a list of just 1 item, we still return nothing. And from there, we actually implement the formula necessary for the sample standard deviation. Let's do a few tests. So the standard deviation of a blank list is nothing. The standard deviation of a single item is still nothing. And the standard deviation of our away runs is 3.12. And what we can do with that information is our average is 4.15, and I can subtract 3.12, and I can say our average again is 4.15, and I can add 3.12. And I can say that one standard deviation range of our away team runs for the 2015 season is 1.03 runs to 7.27 runs. And that gives us a good idea of where the majority of the scores were for away teams in the 2015 season. So in this video, we looked at the mean and the standard deviations of a data set. We implemented the functions. We discussed the sum and the length functions, which were necessary for those functions. And then we did a few examples of how we could find the mean and standard deviation with the functions that we prototyped. In the next video, we will be discussing the median of a data set. The median of a data set is the true middle value of the values sorted. Now, if there isn't a single middle value, such as if there's an even number of elements in the list, we take the average of the two values closest to the sorted middle. In this video, we're going to discuss the algorithm for computing the median of a data set, and we're going to take the traditional approach of sorting the values first and then selecting the values we need in order to compute the median. We're going to be testing the circumstances under which the median function should behave, and then we're going to compute the median of our 2015 away team runs using our prototyped function. When we last left our Haskell notebook, we were discussing the mean and standard deviation of runs, and we found that one standard deviation range was 1.03 to 7.27. Now what I would like to do at the very beginning of our notebook is to add yet another import, and we're going to import data.list. This is where we find the sort function, and I'm going to, as usual, restart and rerun all so that everything is properly loaded for our notebook. Great. I'm going to create a couple of quick lists just to demonstrate the sort function. So here we have odd list. This is 3, 4, 1, 2, 5. Great. Now let's do even list. And even list is going to be 6, 5, 4, 3, 2, 1. We can use the sort function to sort these lists. Pretty straightforward. That's found in the data.list library. If I wish to find the middle value of a list, I need to find the length of the list and then divide by 2. So I can use length odd list and then div 2, and it produces 2. Good. Now I can sort that odd list and pull out the second element, and I get 3. And 3 is the median of our odd list. And for an odd list, that's all you have to do. You should notice that whenever we pass an even list, we get the index position that appears after the median. So if I say length even list div 2, I get 3. And the index position for 3 in our sorted even list will be 4, which is not the median. So we need to take the two values that are closest to the middle, which in this case it will be index 3, and then the index position before that, which is 2, and then add those together and divide by 2. So the formula comes out to being sort even list 3 plus sort even list 2. I believe my parentheses are off there. And then I divide by 2. And I see that our median is 3.5, which is the true median of our even list. There are algorithms for finding the median that do not require the full sort of values, such as you can use the quick select algorithm to quickly find the median sorted value in a list. But for our purposes, we're going to stay with the traditional sort the values first approach. We're going to prototype a median function utilizing the approach that we've outlined here. We're going to go over a few quick examples of what should happen whenever median is called. So here is our median prototyped function. Notice that we are bounding our inputs based on type real, and we are packaging once again a double inside of a maybe. And we're using double because there's the possibility that even though we have a full list of integers, we still need to return a double because we have an even number of integers. If we have a median of no items, then we return nothing. Other than that, we are going to have the possibility of an odd list, then we will return the middle value. Otherwise, we are going to return the middle even. And here we have all of the different circumstances outlined. So what should happen whenever we return the median of an empty list? We get nothing. Likewise, if we get the median odd list, we should get back 3. Notice it's been converted to a double. And if we do the median of an even list, we get 3.5. And to outline again, we have our middle value, which is just the middle index, and we have the before middle value, which is the middle index minus 1. And the middle even is simply those two values divided by 2. And that's all there really is to it. We're using the odd function in order to look for an odd number of elements. Otherwise, we're going to use the even approach. So, using sort, we built a function for finding the median of a list. So this was a long function, and we described it in detail. So finally, we need to use the median function, which we have prototyped, in order to find the away runs. So we found that the middle sorted value of away runs in the 2015 season is 4. In our next video, we're going to discuss what is probably the simplest of the descriptive statistics to discuss, and that is the mode, but it turns out to be one of the more difficult to compute. The mode is the value in a list which appears the most frequently. In this video, we are going to discuss an algorithm for finding the mode. So in this video, we're going to take a look at understanding how the mode of a list can be solved using run-length encoding. We're going to break that problem of run-length encoding into parts and then write the code for our function. We're going to use run-length encoding in order to find the mode of a dataset, and then we're going to compute the mode of our 2015 away runs dataset. I am in my virtual machine, and I need to go back up to the very top of my baseball dataset, and I need to do yet another import. This import is going to be import data.org. We need this for a function that we'll use later on in this video. Now let's restart and rerun all. It'll take a moment. There we go. Great. Now let's create a list called myList that we will use in order to demonstrate the mode. So imagine we have a list consisting of the values 4, 4, 5, 5, 4. Now the value that appears the most frequently in this list, of course, is 4. Now what I would like to introduce an algorithm known as run-length encoding. Now run-length encoding is an algorithm for lossless compression. It has a few interesting applications to it. Now, we can find the mode of a list by first writing run-length encoding. And in order to find run-length encoding, we need to understand how elements group together. So there is a function in data.list called group. And with group, we can create list of list. And each sublist in our primary list is a grouping of the values. And so here we have my list, and then we have group my list 4, 4, 5, 5, 4. Now, what we can easily do is this grouping and count each element in the sublist, thus creating a run-length encoding. So let's create a function to represent run-length encoding. So we need this to be of type for our values. We're going to accept any element as input, and then we are going to return a list consisting of a tuple of those elements followed by an integer, where the integer is going to represent the number of sub-elements in that list. So run-length encoding is going to be whatever list we get in, we are going to map over that list. With that sublist, we will first get the head of the list, and second, we will get the generic length of XS. Now, once we get that generic length, we're going to compute the group. So there we go. So if I pass in run-length encoding of our myList, I compute the run-length encoding of our original list, where each element in order represents the element that is seen and how many times that element is seen. So 4, 2, 5, 2, 4, 1. There will be an even number of elements. And for convenience sake, we group them in tuples. If I do run length encoding with an empty list, I get back an empty list. But here's where it gets interesting. If I do run length encoding, and I first sort my list of values, I now have a tuple of values where all of the 4s are grouped together and all of the 5s are grouped together. I have 3 4s and I have 2 5s. Now what I can do is I can perform run length encoding on the sorted version of my data set and then look for whatever tuple has the highest second value. So this next algorithm computes the mode of a list using the run length encoding function. And here we are using a function called maximum by. And maximum by is found in the data.org library, and it requires that we are comparing based on whatever the second value is, that is the SND. And we are comparing on whatever that integer is, which, as we identified earlier, is the length of a sublist. All our mode function does is sorts the values, passes that data to run length encoding, and then finds which element in the list has the highest second value, thus representing the mode. So if I pass in an empty list to my mode, I get back nothing. And if I pass in mode my example list from earlier in this video, I get back just for 3. So the first element in the tuple will be the most frequently seen element, and the second element is how many times that element is seen. 4 is seen 3 times. Now we've been working with a baseball data set, and we have our away team runs, and now we can find which away team run appears most frequently in the 2015 baseball season. So mode, away runs, and we see that the answer is 2. There were 379 games in the season in which 2 runs were scored, and that is the most frequently seen. So in this section, we recall data stored in a CSV file using the text.csv library, and we implemented the descriptive statistics functions for the range, mean, median, and mode, and standard deviation. These functions will become our descriptive stats module for future sections. In our next section, we will begin using SQLite 3. SQLite 3 is a file format for storing data in the same mindset of a relational database, such as Oracle, MySQL, MariaDB, and Postgres. While I suppose that you could use SQLite 3 as a traditional database engine, it's really not made for that. SQLite 3 allows us to open up a file, work with the data in that file using SQL statements, and then close that file. One file can contain one database, and a database can store multiple tables of information. Contrast this with the CSV file format, which we used in the last section, and CSV file formats, at best, store a single table of information. The advantages of SQLite 3 are that it doesn't require any server-side programs running in the background, there are no configurations to discuss, and the executable for working with SQLite 3 is a single file. So, in my opinion, working with data in a SQLite 3 file format is more versatile than working with data in a CSV file format. In this section, we'll focus on how to get our data from CSV into SQLite 3. Then we'll be training ourselves to think of our data set in terms of a database using SQL statements to fetch data. This requires an understanding of select queries. We do need to craft some code for translating the output from our select queries into Haskell, and we will demonstrate how to use our data summary functions from section 1 with our database. So this video is going to be a primer on SQLite 3. There's actually not going to be any Haskell code in this video. We're going to take a moment and translate a CSV file into SQLite 3. In this video, we're going to take a look at introducing SQLite 3. We're going to create a table in a SQLite 3 database, and we're going to add a CSV file to that table that we created in our SQLite 3 database. So from here, I would like to move over to my virtual machine for our Haskell environment. I already have my web browser open, so I've got the Google website open up, And what I would like to do from Google is to do a search for USGS Earthquake Feed CSV. USG is the United States Geological Survey, and they keep a database of every single earthquake that takes place on planet Earth. And they offer this data in CSV file. So we're going to click that very first link. You should see spreadsheet format at the top of the first link. And I'm going to scroll down to the heading over here that says past 7 days, and I want to find all earthquakes. And I will have the option to download the all-week feed for all earthquakes that have happened in the past 7 days in the United States. So let's save that file. Let's go over to our terminal, and I'm going to do ls, and I see that we have in our downloads folder an all_week CSV file. That's the file that I just downloaded. And what I would like to do is to convert this file to a CSV file. And let's take a look at the file. You can see that this particular file has a header line, and we can look at the header information of all of our columns. The first 5 pieces of information on every record will be the time, latitude, longitude, depth, and magnitude. And there's a lot of other information here that we could go through. But for our purposes, I just want those first 5 columns of information. What we can do in order to narrow this data set down to just those first 5 columns of information is to use a command called cut. Cut's a very useful command for working with CSV files. And we have to pass it a delimiter. And the delimiter is going to be a comma because this is a comma separated value file. And we need to know what fields that we would like to keep from our file. And I said that we want the first 5. And so we type in 1, 2, 3, 4, 5, and we separate them all from commas. And now I pass in my file name, and I'm going to name this earthquakes.csv. Now that file, as you recall, had a header line, and we need to chop that header line out of the file. So there is another tool that we could use in Linux, and it's called tail. If I type in tail-n +2 earthquake CSV, I'm going to create a temporary file. That e.temp file will be our original file of earthquakes.csv, but without that header line. And now I can move my temp file over my earthquakes file, and this is the primed data set that I would like to use. So let's take a look at earthquakes.csv. This is all of the earthquake data over the past 7 days. I can see that there are 1,585 earthquakes represented in this data set. And we have the first 5 columns of information, which is the time, latitude, longitude, depth, and magnitude. Next, I need to install SQLite 3 and the SQLite 3 development library. And in Debian, the command for this is sudo apt-get install SQLite 3, and then I want lib SQLite 3 dev. Great. Now that SQLite 3 is installed on my system, I want to create my first SQLite 3 database. Typically, SQLite 3 database files end with the extension SQLite 3. And since this is a database from the U.S. Geological Survey, I'm going to call my database USGS SQLite 3. SQLite 3, USGS SQLite 3. That just created the database file on our hard drive. There's nothing in that file. There are no tables. What we need to do next is to create that first table. I already have the command in my clipboard for creating that first table, and I want to describe what this command does. We're going to create a table called earthquakes, and then I'm going to pass in the 5 columns from our file, and I'm going to name them time, latitude, longitude, depth, and magnitude. Now the first field is going to be of type text, and so I put the word text after time, but the remaining 4 fields are all going to be based on floating point numbers, and so I use float type for those 4 types. This now has created the table in our usgs.sqlite3 database file, but it doesn't have any of the information in that table. What we would like to do is to import our data from CSV into SQLite 3. we need to tell SQLite 3 in order to read from CSV. And the command for that is mode CSV. Next up, we need to perform the actual import. So the command is .import, and then I type in earthquakes.csv, because that was my earthquakes.csv file. And then we need to tell it the name of the table, and I named my table earthquakes. Great. If you didn't get any error messages, good job. This means that you have created and imported all of the data from our past 7 days USGS earthquake feed into an SQLite 3 database. What I can do now is run a select query on here. So let's do a really simple select query. So select everything from earthquakes, limit 5. And what this means is I want 5 records from our database, but I really don't care which records they are, and give me all columns from those records. So those are the typical results I see. Now in order to get out of this interface, I hit Control D on the keyboard. So great. If you've gotten this far, you should see a new file on your folder called usgs.sqlite3, and it will have a little bit of information in it. If it's not the exact same size as mine, don't worry. There's going to be a different number of earthquakes going around the earth depending on when you view this video, so your size of the file more than likely be different from mine. But you should have a few thousand earthquakes in that database. So let's pretend that we're working with multiple CSV files. We can repeat our steps in this video and create a table in our SQLite 3 database for each CSV file, and then import each CSV file into that database. This allows us to package many tables of information into a single file that can be represented with a clean, consistent interface. So SQLite 3 has lots of advantages, but it's not enough. We need a language like Haskell for serious number crunching. In our next video, we will be discussing how to work with SQLite 3 and Haskell. Our last video discussed how to convert a CSV file into a SQLite 3 database. This video will be about getting data from SQLite 3 into Haskell. In this video, we're going to be taking a look at understanding the basic types within SQLite 3 and their Haskell counterparts. We're going to be installing the necessary software in order to get Haskell and SQLite 3 to communicate with each other. And we're going to be writing a few select queries within Haskell. So there are a few different data types in SQLite 3, those types with their Haskell counterparts. The 4 primary types are integer, real, text, and blob. And text and blob are almost the same types. I believe that one is for raw data and the other is for string data. But we can interpret both of those in Haskell as string. Integer corresponds to integer, real corresponds to decimal. There is a 5th type in SQLite 3 called numeric, which is adaptive and is treated as an integer with integer data and a real with real data. And for those instances in which you have a column with both, I recommend that you don't use numeric at all and you just use that real column heading. Now we're going to go back to our virtual environment for running our Haskell notebooks. I have my terminal open to the directory code Haskell data analysis, and I have 2 folders under my Haskell data analysis folder, analysis and data. What I would like to do is to move my database, which we created in the last video, into that data folder. So I'm going to copy from downloads the USG SQLite 3 file into our data folder. Alright, that's it. What we need to do now is to install the necessary software to get Haskell and SQLite 3 to communicate with each other. We need a few drivers. So sudo apt-get install libghc hdbc SQLite 3 dev. Alright, looks like I've already installed that one, but that is the command to install that particular library. We're going to be needing it for our work coming up. We also need a few libraries from Cabal. So Cabal install HDBC and HDBC SQLite 3. So Cabal takes a little bit and it's going to download and install those libraries into our home folder. Great, we're ready. So I am going to start our Jupyter notebook with Jupyter Notebook. Inside our analysis, I'm going to create a new Haskell notebook, and this will be renamed Earthquakes. Great. Let's go ahead and import our database tools. So import data.list, import database.hdbc.sqlite3, and import, I said 2 instead of 3, and import database HDBC. Great. And with that, we should be able to connect to our SQLite 3 database. Now, hopefully you have put your data in your SQLite 3 database into the data folder as we did before turning on our notebook. Let's create a connection to our database. And so the command for creating a connection to the database is connect SQLite 3. And then we pass in the path of our database file as a string. If you didn't get an error message, that means the connection was made and you should be ready to go. Let's issue our first query to see if we get back any data. This will be a similar query to what we did in the last video, except we'll be doing it from within inside of Haskell. So let's do records, and the command for a quick query is quick query. We need to pass in the first argument is the database connection, so quick query DB, and then we'll pass in our select. So we're going to select everything from earthquakes, and we're going to limit that response to 5 records. And we need to pass in an empty list, and this list, which I am including on the end, is a way of passing in arguments into the select query. I've got a really simple query, so I'm not using it, but I still need to have that empty list there. So that's the purpose of the empty list at the end of the quick query call. Let's take a look at what is returned by records. You see that we have a list of records here. Let's make sure that we get 5, because that's how many we specified in the SQL query. LEN. Good, we get 5 records. Similar to what we did in our first video, we're going to create a quick function using the function from SQL in order to parse data from a column into a more familiar double type. So let's create our quick function. This will be named readColumn. And all we're going to do is call map from SQL. And we're going to produce this partial function called readColumn. Now there is another function in data.list called transpose, and it allows us to perform essentially a matrix transpose on a 2-dimensional data type, which records is. This allows me to pull a record as an entire row from the data set. So the 4th column in our data set is the depth. And if I do a transpose, I could say, give me the 3rd row, because all indices in Haskell are 0-based. So if I do read column transpose records, I'm going to say, give me the 3rd one, and we're going to read this as type double. We now have the depths of the 5 earthquakes in this particular data set. In the next video, we are going to examine the essential features of the select query that make it so useful. If you're already a whiz at SQL, you should be able to safely skip this next video. If SQL is unfamiliar to you, then sit tight. You're going to be learning about how to slice up data with SQL in the Haskell environment. This video will be an overview of the versatility of the select query in SQLite 3. Most of the content of this video will pertain to the inner workings of the select query and not the Haskell language itself. So in this video, we're going to have an understanding of the following select clauses: where, order by, and limit. Each of these have their own utility, but when these clauses work together, you can quickly see how data can be sliced into workable chunks that can be studied later. This is my preferred way of working with data. Let SQL do the slicing and Haskell do the dicing. Once we have a data slice that we're happy with, we'll spend some time at the end looking at how to parse that chunk of data into something usable by Haskell. I am back in my virtual machine running the Jupyter notebook. I'm going to swap over to my primary earthquake notebook. We're going to begin with a simple question. If our data set of worldwide earthquakes is truly worldwide, shouldn't there be a nearly equal number of northern hemisphere earthquakes and southern hemisphere earthquakes? Only one way to find out. An earthquake is in the northern hemisphere if it has a positive latitude. So let's start by counting the number of earthquakes that meet the criteria of having a positive latitude. We're going to call this the northern data set, and we'll say quick query db select all from earthquakes where latitude is greater than 0. Let's look at the length of that northern query. All right, over 1,000, 1,530. That seems like a lot. Let's do the same for earthquakes in the southern latitude. This is going to be relatively straightforward. We're just looking for earthquakes with a negative latitude. All right, and the length of our southern earthquakes, there's only 55. So that's nowhere close to being equal. And what could account for these differences? So in working on this video, I personally contacted the U.S. Geological Survey and asked them to explain this discrepancy between over 1,000 earthquakes in the northern hemisphere and less than 100 in the southern hemisphere. The reasoning I got back was that there are simply more earthquake monitors in North America, hence there are more earthquakes recorded. And that's really all there is. Since we're on the topic of North America, let's record how many earthquakes are in the northwest hemisphere. And that will require that we look at all of the earthquakes with a positive latitude and a negative longitude. So this is an instance where we get to use the AND Boolean operator. So we're going to call this northwest, and we'll issue a quick query, select star from earthquakes where latitude is greater than 0 and longitude is less than 0. All right, so let's see how many northwest earthquakes we have. 1,477. Since we know there's not going to be many earthquakes in the southwest hemisphere, let's go ahead and look at the magnitude and depth of those earthquakes. So first I'm going to get the southwest earthquakes. All right, so select star from earthquakes where latitude is less than 0 and longitude is less than 0. All right, so how many earthquakes are we talking about? Not many, only 28. So what we can do from here in looking at the Southwest data set is do what we did at the very end of the last video where we performed that transpose to look at the depth information. I can say read column, transpose the Southwest, and I'm going to pull the third information, and I'm going to say read that as a list of doubles. And there is all of our depth information. I can look at this again, and I can say get the fourth column. Those are all of our magnitude information for earthquakes in the southern hemisphere. Now you'll notice that there doesn't seem to be any order to our information here. So let's do another Southwest query. I'm just going to copy and paste this. And we're going to do what's known as the order by. So we'll order by magnitude. So now our Southwest is going to be ordered by magnitude. If I read this fourth column again, you can quickly see that the smallest magnitude earthquake in the Southwest Hemisphere was 4.2 and the largest is 6.0. By combining with the limit command, I can say order by magnitude, and then I can add a limit 5. So that simply means order by magnitude, but take the first 5. So now whenever we read our columns again of the Southwest Hemisphere, we should only get 5 values, and they're going to be the 5 smallest value earthquakes. But what if we want to flip this on its head and get the 5 largest earthquakes? Well, that's a simple change. We're going to expand on our query statement once again, and after the magnitude call, but before the limit, I'm going to add DESC, and that stands for descending. So it's going to sort the magnitudes from largest to smallest, and then take the first 5. All right. So we're going to mold that statement again, and to demonstrate how this works, we see the top 5 magnitudes. So in this video, all we did was we took the select query and we started molding it using the where clause. After we experimented with a few circumstances in which we sliced up the data with where, we began to sort that data based on one of the columns, and in this particular instance, it was by magnitude. After we looked at how we could order by the magnitude, either from smallest to largest, which is the default, or from largest to smallest, and that requires us to add the descending call, we can get a finer grain selection to our data. And with the limit call, we can prevent ourselves from getting so much data that we can't work with it. If you feel like you're getting too much data, you can add that limit to your select query. Haskell but Haskell can handle as much as you can throw at it depending on the memory of your system. So there we go. In our next video, we will be looking at how to incorporate our descriptive statistics module with the material that we've covered in this video. So far, we've seen how to generate a SQLite 3 database using the SQLite 3 command line utility and how to interact with that database within Haskell. This video combines the knowledge of descriptive statistics from Section 1 with our database work in Section 2. In this video, we will be using descriptive statistics with our SQLite 3 database. First, we will create our descriptive statistics module from functions found in our baseball notebook. Second, we will slice up some data using select queries. Third, we will pass data to our descriptive statistics functions and discuss the results. We'll be looking at earthquakes specifically in the region of Oklahoma. So let's slide over to our virtual machine running our IHaskell notebook. And what I would like to do is to discuss how we can take the functions which we wrote in Section 1 related to our baseball data and how we can use it here. So I am in my analysis folder in which I keep all of my notebooks, and I have added a file called descriptivestats.hs. I'm going to highlight the file right there. And you should create a file called descriptivestats.hs, and you should take all of the functions which we wrote in our baseball notebook and add them to this file. And I'm going to show you what this file looks like. So I've already taken the liberty of doing that. I've got our range function, mean, standard deviation, median, count leader, count pairs, and mode. So these are the functions which we wrote. Now in order to make this a full-fledged module, we're going to add our module line. So module, descriptive stats, where. I need to add the essential import statements which these functions utilize. So import data.list, import data.ord, and import data.maybe. Great. Now, once you've completed that, you should have your descriptive stats module ready to go. So I'm going to go over to our notebook, and I am going to scroll up to the very top, put my cursor in the very first cell up at the very top, and I'm going to click on Edit and Split Cell. And that's going to create a new cell before my import statements. Here, I'm going to load our descriptive stats module. In our next block, I'm going to add another import line where we import descriptive stats. Now that I've loaded the descriptive stats module and imported it, I'm going to click on Kernel and restart and rerun all. This is going to reset the notebook and load our descriptive stats module and re-import all of our imports. It's going to take it a moment to wake up, and we're going to see it run. Great. If you got any error messages from this step, chances are you mistyped something in the descriptive stats.hs file. You can always pull the descriptive stats.hs file that I will be providing with this video series. All right, we're all set to go to try to answer a question. So what I would like to do is look at the state of Oklahoma. There are many earthquakes around the world. We could simply compute the average over all of them in the past week, but I would like to focus in on Oklahoma. Oklahoma exists between 33.5 degrees north and 37 degrees north, as well as 94.3 degrees west and 100 degrees west. That's that straight line right there. And for those of you who know about the shape of Oklahoma, I'm ignoring this rectangular portion known as the Panhandle, and I'm focusing just on the mainland which encompasses most of the earthquakes that you see right here. I'm going to zoom out a little. Now, earthquakes in Oklahoma are an interesting phenomenon. Historically, major earthquakes don't happen in Oklahoma, but Oklahoma is a special case. Recent years have brought the practice called fracking to Oklahoma. Fracking damages the earth, and it's believed that this is the cause of the increase in earthquakes. While we don't have access to years of data in our 7-day database, let's look at the magnitude of Oklahoma earthquakes compared to non-Oklahoma earthquakes. Now, to make this easy, I already have a query ready which represents the state of Oklahoma. I'm going to paste it here into the box and explain the query. So Oklahoma is going to be a connection to our database. We are going to select from earthquakes where the latitude is from 33.5 to 37, and the longitude is from negative 94.3 to negative 100. Now, what I've noticed in the U.S. Geological Survey database is that sometimes the magnitudes will appear blank. And so I have a call here, magnitude is not blank. And I'm going to hit Shift Enter on this query, and we're going to see how many earthquakes we get. So link Oklahoma, 33 earthquakes. What I would like to do now is to get everything that's not in the state of Oklahoma. So I'm going to copy my Oklahoma query, I'm going to paste it, and I'm going to make a few changes here. So we're going to change this to not Oklahoma, and I'm going to introduce a new function, not, and I'm going to wrap all of the latitude and longitude coordinates in parentheses. I still include the and magnitude is not blank, but that's outside latitude and longitude coordinates. So what this does, it's going to say if a earthquake exists inside the state of Oklahoma, we're going to exclude it. But if it's outside Oklahoma, we're going to include it. So let's run that query and see how many non-Oklahoma earthquakes we get. 1,549. Good. Now in our data set, we know that the fourth column, remembering that the first column is really the 0th column. So column number 4 is our magnitude, and we can specify this. I'm going to say OK mag is equal to read column transpose Oklahoma 4. We're going to read this as a double. We also know that our non-Oklahoma earthquakes, not Oklahoma magnitudes, comes from not Oklahoma, and it's also on the 4th. Now here's where I believe that we can have some fun. We simply pass these lists, OKMag and not OKMag, to our functions found in the descriptive statistics module. So I can say mean OKMag, the average magnitude earthquake was 2.84. And we can say not OKMag. Outside of the state, it was 1.47. So earthquakes inside of Oklahoma have a higher magnitude than earthquakes outside of Oklahoma. Now, does this stack up with the information provided by the median? Now, the median gets the true middle based on the amount of data that we have. 2.7 for inside of Oklahoma and 1.2 for outside of Oklahoma. Now, which of these two states has the larger variation of earthquake magnitudes? Let's find out. So standard deviation, OKMag. We see a standard deviation of 0.58 if we round, and then standard deviation, not OKMag, 1.19. So there's a higher standard deviation among non-Oklahoma earthquakes as opposed to Oklahoma earthquakes. And while we're at it, we're testing out our functions. Let's go ahead and test out the mode function. So what is the most frequently seen magnitude across all of our data for the two data sets? So mode, OKMag, 7 earthquakes have a magnitude of 2.5, and 47 earthquakes have a magnitude of just 1.2. There we go. We could further slice up our data based on the depth of these earthquakes, and we can study that information. But I believe that this is a good example of how to use descriptive statistics with the SQLite 3 database. It's time for our section summary. So in this section, we installed the SQLite 3 command line utility and installed the necessary SQLite 3 libraries for working with data in the IHaskell environment. Most data doesn't come in SQLite 3 format. Most data comes in that CSV format. So we covered how to convert a CSV file into a SQLite 3 table. We explored the versatility of select queries in SQLite 3 by means of the where clause, the order by clause, and the limit clause. We also explored how to create our own custom module of descriptive statistics, and then we used that module in order to study earthquake data in the IHaskell environment. Now, in our next section, we are going to take a look at regular expressions in Haskell. The purpose of regular expressions are to represent a pattern that can be identified within some text data. In the context of data analysis, there are a couple of important uses for regular expressions. One, to validate fields to make sure that all values within a particular column adhere to a particular format. And two, to search fields based on a particular pattern. Word processors and editor applications have a find and replace feature. You submit a bit of text to identify within a larger bit of text and the desired replacement. The application will replace all of the found text with the desired text. Many of these applications now include regular expression support. Rather than submitting an exact sequence of characters which need to be found, we submit a pattern. This pattern defines what is considered valid or not using regular expressions. So regular expressions are a mini language. They aren't limited to the Haskell language. Once you understand regular expressions, you should be able to translate that knowledge into other programming languages. Each programming language may implement the mini language of regular expressions with slight variations, so you'll need to properly test your expressions when moving from language to language. In this section, we are going to take a look at understanding the mini language of regular expressions. That includes dots and pipes, atoms and atom modifiers, and character classes. In the last two videos of this section, we are going to use regular expressions in real applications, such as looking at regular expressions with a CSV file and looking at regular expressions with a SQLite 3 database. So in this video, we're going to cover two basic bits of regular expression syntax, and those are dots and pipes. So to begin our video, we are going to install the regular expression library in Haskell, and we are going to introduce the dots and the pipe syntax. So let's get started. I'm going to move over to my virtual machine, and let's find the terminal. And we need to begin by installing the library, and that is done with cabal install regix POSIX. It'll take a moment for this library to install. Great, we're done. Let's create a new notebook and dive in. So I'm going to begin a new notebook. I'm going to rename this regix learning, and we need to import the text regix POSIX library, and that will give us access to the equal tilde operator, which is necessary to look at regular expressions. Let's define a couple of strings in order to get us started. String 1 is going to be 1 fish, 2 fish, red fish, blue fish. It's the title of a popular Dr. Seuss book that I like to use when teaching regular expressions. And our second is going to be a classic, the quick brown fox jumps over the lazy dog. All right. Now that we have a couple of strings and we have our library imported, we now have access to the equal tilde operator, which can be used to evaluate if a pattern exists in a string. So let's do a quick couple of examples. This is going to be a very simple, does a string exist inside of another string? And so str1, I can say equal tilde and say 1. And what we're asking, does the substring 1 exist inside of str1? And we can quickly see, yes, it does. We're going to do this again with string 2. Say, does the string 1 exist in string 2? No, it doesn't. All right, so let's go over our first bit of regular expression syntax, and that is the dot, also called the period. So the dot matches any one character. So we know that the word 1 exists in string 1, but what about a different expression? So if I say str1 o.e, bool. And so what we're asking, does the sequence O followed by the character E exist in string 1? Well, we already know one O-N-E exists there, so yes, this should evaluate to true. We could do the same thing again with str2 O.E. Now, does that sequence exist anywhere in the string? And that also is true because the letters OVE exist inside the string. I'm going to highlight OVE, the match inside this string, and that's what's matching in string 2 in order to resolve this as true. The dot matches any single character. The second regular expression character that we would like to introduce in this video is pipe. The pipe character is made using the vertical character or bar that appears over the enter key on most keyboards. Many programming languages use the pipe to represent or, and regular expressions is no different. We can put a pipe between two expressions, and that means that either the first or the second expression is valid. So let's do a quick example. So str1 tilde, does the word fish or fox appear in a string? Fish, fox. And we know that the word fish appears several times in our first string, so yeah, this is going to be true. We could also do the same with str2, fish, fox. We know that the word fox appears in our second string, so of course this also results in a true. We can look again at dog or cat in our first string, and that is false. And we can do the same with our second string. So dog or cat do not appear in either string, so both of these are going to result in false. So in this video, we installed the regular expression library, and we looked at two symbols within the regular expression syntax, the dot and the pipe. The dot represents any one character, and the pipe means that any two expressions can be true. I didn't demonstrate this, but we can also chain multiple expressions with pipe so that any one of the expressions in the pipe chain can be true. In our next video, we will be looking at simple modifiers with regular expressions and understand what an atom is. We will be expanding on our knowledge of regular expressions in this video by discussing the atom. In this video, we will cover the concept of an atom. An atom is a single expression, such as a character or the dot, or an expression that has been defined using parentheses, or, as we will see in a future video, the character class. We will also introduce atom modifiers. The idea is that you can take any atom and then modify it using a modifier. I'm back in my virtual machine. I have my Regix Learning notebook up from the last video. Let's begin. An atom is a single character or an expression that has been defined using parentheses or as a character class. Imagine that you have a string representing a date in the year, month, day separated by dashes format, and you wish to verify that this date is in the 1900s or the 2000s. So let's say that we have a date of 1969, July 20th. And we wish to verify that this date is in either the 1900s or the 2000s. Well, we could craft a regular expression based on an atom of 19 or 20, followed by a series of dots and then dashes separating those dots for the remainder part of the string. Say if that's a bool or not. Great. Let's say that we have a different expression that is 18 AB 40-99. So this is another date that could potentially enter into a system through whatever stretch of the imagination. And let's see if this has the potential of meeting our same regular expression. Good. That one is false. As you can see, this regular expression only validates the first two digits with the 19 or 20 atom. This isn't a perfect regular expression because it doesn't validate the entire date, but we'll build on this particular expression in future videos. Hold on to this example, it will get better. But this idea lends itself to the concept of atom modifications. So with atom modifiers, we can specify how many times an atom should be repeated inside of an expression. I'm going to change this next block to a markdown. we can modify any atom using symbols after the atom. For example, how do you spell the word color? All right, I'm going to say spellings. How do you spell the word color? Well, I'm an American, so I spell it color. But there are other parts of the world that spell it color, C-O-L-O-U-R. But we know for a fact that this is wrong. We can say color. Well, that last one is wrong. Using the question mark regular expression, we can specify that the U is optional and that either spelling, either with the U or without, is legal, as long as that U appears after the O. So let's define our regular expression. I can say color, there's the American spelling, C-O-L-O-U question mark R. That question mark appears after the atom U, meaning that the U is now optional. And so we say, yeah, that's true. I can take this expression again and say C-O-L-O-U-R, and this expression is still true. And then I can misspell the word. I can say U-O. And now this one is false because the U didn't appear in the correct place. So here's our next two modifiers. For example, imagine that you have a pattern that requires that we match a string containing any number of ones followed by any number of twos. The asterisk character means that an atom must appear at a minimum 0 times or many times. So let's give an example. I can say 1122, and will this match a pattern of any number of ones followed by any number of twos? And yes, that's true. But let's say I just have an empty string. Will that also meet the pattern of any number of ones followed by any number of twos? Yes, it does, because any number could also mean 0. What if I just leave one out? For example, 111. Any number of ones followed by any number of twos. Well, yes, that's true also. What about something that has nothing to do with ones or twos at all? So ABC. Any number of ones followed by any number of twos. And yes, all of these are true. In fact, you'll notice all of these expressions which I've gone through are true. It's not possible for me to write a string that fails on this particular regular expression. Now let's change this up and say that the ones and twos in this string have to appear at least once, but they can still appear any number of times. Well, we just change those asterisk characters to plus signs. So 1122, 1 plus 2 plus. Good, this is true. But if I leave out one character or the other, you'll see that this is false. At a minimum, I must have one of each in order for the expression to be true. All right. Finally, there's what's known as the custom modifier, and this allows you to create custom specifications based on any number of repetitions. So here's a convoluted example. Let's say that we want the number 1 followed by the number 2, which must appear between 3 and 5 times, followed by the number 3. So if my string is 1, 2, 3, I can specify this as 1, 2. And in order to create a custom modification, we say in curly braces, the high, comma, and the low. So this says that the 2 must appear between 3 and 5 times. And we see that the 2 only appears once in our original string, so this fails. If I repeat this again with just 2 2's, we see that's also false. But once I enter 3 2's into my expression, well, this one is now true. And because this is a custom modification where we say at most 5, if I enter 6 2's, well, then this is going to fail. So here are the 4 modifiers that we've covered in this video. We've covered the question mark, which can appear 0 or 1 times. We've covered the asterisk, which can appear 0 to many times. We've covered the plus sign, which can cover 1 to many times. And then we have the custom, which is based on your own criteria. So here's a few rules to remember. Any expression that's been modified with a minimum number of 0 required matches, such as the question mark, the asterisk, or a specified modifier with minimum matches, will always evaluate to true. And you need to be mindful of your expression so that if all of your atoms are modified in this manner, then your expression will always be true. And then your expression is not useful to you. So in the next video, we are going to introduce character classes. Character classes are a way of combining characters with common traits into a single classification, such as the characters that represent numbers, or letters, or vowels, or hexadecimal characters. Once we get into the details, we will see how useful character classes are. So in this video, we're going to take a look at introducing the basics of character classes. We'll expound on that by introducing character class ranges, and then character class negations, and then we will write a full regular expression to handle matching dates. So our first introduction to character classes begins with vowels. Vowels are the letters A, E, I, O, U. Almost every word has a vowel in it. Let's see if we can write a character class that matches a vowel. So here is the word dog, and to begin a character class, we use square braces. So A, E, I, O, U are our vowels, and we're going to match that to a bool. Now, a character class means that a letter must match one of the letters that exist in those square brackets. Yes, and there is a vowel in the word dog, so this results in true. What about the word Y? A, E, I, O, U. And this turns out to be false. There are no vowels in the word Y. As long as one character inside the character class matches, the entire character class matches. We could create a character class for numbers. So in the string 1, 2, 3, we could ask, does that string contain any numbers? This will require us to create a character class consisting of the digits 0 to 9. That's true. Let's do the same thing with dog, and we see that's false. We could also create a character class for letters of the alphabet, where we would type A, B, C, D all the way to the letter Z. But that would be very error-prone. If you missed a letter, that letter would never be matched in the character class. For this reason, character classes support ranges. Inside of the character class, use a hyphen between two characters, and you will get all of the characters from the first character to the second. As you can see in our examples, character classes are not case-sensitive. So let's go through a few examples. So in the previous example where we did 1, 2, 3, and we matched it up with all of the number characters, we could write that as 0 to 9. That's true. We could also say, does the word dog, lowercase d-o-g, contain any lowercase letters? Of course, it does. So this should result in true. Does the word dog, lowercase d-o-g, contain any uppercase letters? We see that it does not. So in order to find words with mixed cases in a character class, you simply repeat two ranges back to back. So D, O, G, and then we can repeat that range twice, once for uppercase and again for lowercase. That's true. One more feature of character classes needs to be expressed, and that is the negative character class, which matches to any character not found in the character class. To make a negative character class, start the first character in the character class with the caret. So does the word Y contain any constant sounds? We could express that as Y. And here we are going to begin a character class, and the very first character in that character class is the caret, A, E, I, O, U. So this means not vowels. In other words, anything that's not a vowel. And yes, there are characters which are not vowels in the word Y. What about any symbols that aren't letters of the alphabet? There is a singer in America by the name of Kesha, and Kesha spells her name K-E$HA. What we would like to ask is, does Kesha's name have any non-letter characters in her name? We can say not A to Z, A to Z, first uppercase, then lowercase. And yes, she does. So remember in our last video where we talked about how to express a date, and we talked about expressing a date that only works for the 1900s or the 2000s. So let's say that we have a date 1969-07-20. And we would like to express that if that truly is a date. Well, here in my clipboard I have a regular expression to match a date, and I use lots of character classes to make sure that we have the numbers to make sure that we put numbers into our expressions correctly. So we begin with a 19 or a 20 followed by two numbers and then a dash and then two numbers and then a dash and then two numbers, and that's where we end. Let's see if that works. That's true. So let's play around with this expression. I'm going to copy this expression. And we're going to say, does the date 1901 4099 match this expression? Now we say that is also true. So this doesn't perfectly work for all dates. Let's see if we can modify this any so that we resolve this to be false. Now a month can only be the numbers 0, 1, all the way up to 12 for January to December. So I'm going to take out the month portion in our regular expression, and I'm going to modify this a little bit. So we can say 0 followed by a character class of 1 to 9, or a 1 followed by the character class of 0, 1, 2. So here we have a character class that matches just the digits 0, 1 all the way up to 1, 2. Now this still doesn't work because we have the 99 on the end, although that still results in a false. Now in order to get that last date, we need to make sure that we only allow for days of the month that go from 0, 1 all the way up to 31. So let's compound on that. Well, we can have our 0 followed by 1 to 9, or we can have 1 or a 2 that goes from 0 to 9, followed by another or, and a 3, which can have a 0 or a 1 after it. And that is a very lengthy regular expression to match a day of the week. Now we should test this under a variety of circumstances, but I'm going to test this out again with our original date of 1969, July 20. That one's still true. So at least we know that this regular expression works for these two circumstances, and we would need further testing in order to verify this one. Regular expressions can be very hairy, and they can also be very hard to test. But once you figure out the language, you can do lots with them. So in our next video, we are going to use regular expressions in the context of a CSV file. We need to discuss the importance of using regular expressions in various file formats, such as CSV and SQLite 3. Our first video will cover the CSV format. So let's examine a question using one of our past datasets. Using our baseball dataset, let's try to find out the average number of runs scored by away teams in the month of March. To do this, we'll need our CSV file of data, which has the dates in the first column, but it's not organized by month. So in order to solve this, we need regular expressions. So in this video, we're going to be crafting a regular expression to match a field in the CSV file. And in this case, we're going to use that first column of dates. We're going to be pairing that information with another column. And in this case, the other column is going to be the runs scored by away teams. And then we're going to filter that information to get just the information that corresponds to the regular expression. Now what I would like to do is go back over to my virtual machine, and I would like to show off a file that I've created for this video. It's called mycsv.hs. Here it is. So let's look at this file. And what I've done is I've created a module of the functions that we utilized in section 1. In particular, the noEmptyRows function and the readIndex function. I've also included a function called getIndex. Now readIndex is a partial function that allows us to parse data from a column, where getIndex simply returns information from a column as is in the string format. So let's create a new notebook utilizing myCSV. So we need to load up our libraries. So load descriptive stats and load myCSV. Now let's do our imports. I have my imports ready to go in my clipboard to save me from typing it. We will be utilizing the text.csv library. We'll be using data.maybe. Of course, we'll be using regular expressions, and then finally the two libraries which are custom made for this video. Now we need to parse our CSV file, and we're going to use the exact same data set that we used in section 1, the baseball data set. So baseball, parse CSV from file. And now we need to get the game dates. And if you recall, all of the game dates were on the first column. And so that means column 0. So game dates is equal to get index baseball 0. Now let's look at the first entry in game dates. We see the date here, March 5th, 2015, and we see that it's one long string of numbers. And what we need to do now is to craft a regular expression to get just the 04 portion of that. So let's create March date. And this is going to be a Boolean array of length equal to game dates. And it will be true if it's in the month of March, and it will be false otherwise. And so we can map our regular expression function, and we can pass in a regular expression of 04. So we have 4 dots at the beginning because we don't care about the year, and we have 04 because we care about the month of March, and then 2 more dots afterward because we aren't worried about the day. Now we can pass in game dates. We also need the away runs that we've used in past videos. So away runs, read index baseball. If you recall that those are going to be on the 10th column, so we need to pass in 9 for the index. And we'll parse them as integer. And now we need to make sure that the length of March dates and the length of away runs are identical. So length March dates and length away runs, well, they both match, 2,429 games. And what we need to do now is to combine these two data sets. And if I type zip March dates and away runs, you're going to see the pairing of all of this information. I'm just going to let it spill out onto the screen. So you see that you see a series of trues because this is a chronological data set beginning in the month of March. And you're going to see at some point they transition into false because we go into the next month. And the rest of these are all false. So good. I'm going to scroll back up and get my zip statement. So now we need to filter these based on what's true in the first portion of every tuple. So we can say filter FST for first, and then we pass in our March dates. Great. And so now this produces just the list of elements that are in the month of March. You'll see it's a much shorter list, and the beginning of every tuple is true. Now we need to strip out those trues. The true portion is no longer necessary. And for that, we can just say map SND for second and pass in our expression. So there we go. We have all of the away runs scored in the month of March. And finally, we can take this expression and we can pass it to the mean. So I can say mean and I can map it, and I can say there were 4.2 runs on average scored by away teams in the month of March. Hopefully you can identify how this approach can be adapted to a solution which works for every month of the year. With a little more effort, we can examine the month with the highest and lowest average. All right. I should rename this notebook before I exit the video, so I'm going to name this Regix Learning, I'm going to say CSV. In our next video, we are going to use regular expressions with SQLite 3. Working with regular expressions in our SQLite 3 database is no different than working with a CSV file. In this video, we will demonstrate how to filter our data using regular expressions using the timestamp data from a SQLite 3 database in a similar manner to our last video. So we're going to be loading the data from a SQLite 3 database, sifting through that data using a regular expression, and analyzing the data gleaned from that regular expression. Now the problem that I would like to solve in this video is to determine how many earthquakes happen by hour in our 7-day database. Let's go over to our virtual machine and let's create a new Haskell notebook. I'm going to name this notebook Regix Learning SQLite 3, and I will be importing our libraries. I don't plan on using any descriptive statistics in this video, so there's no need to load the descriptive statistics module. There is one import that you see there that we haven't covered yet, and that's text.printf. There's one little problem which I hope to solve using the printf function, and you'll see that coming up. So let's import our earthquakes database that we did in section 2. So db connect SQLite 3 data USGS SQLite 3. Now we need the read column function that will allow us to read data from a column. Now that we have our database ready, we need to pull the raw timestamps. Time raw quick query db select time from earthquakes. And this will pull all of the earthquake times. Now we need to convert these raw time data into a string, which I will call timestamps. So timestamps. We're going to read the column, and we're going to get the head of the transpose of our data. And this will all be parsed into a list of strings. Forgot to put the equal sign in there. Forgive me while I fix that. Great. Now let's examine the first timestamp. So head, timestamps. And as you can see, we have a much more complicated timestamp than what we were working with in the last video. There's lots more information here to work with. So what I would like to do is to extract the hour from each timestamp. And the hour occurs right after the letter T, and it's that first 2-digit number. So here's where the printf function comes in. I would like to take any number and convert it to a 2-digit number as a string with T in the front, and printf does this for me. So printf T $0 to D will do just that, and I can pass in any number such as a 7, and it will convert it to a 2-digit number, 0 padded with T in front. Likewise, I can take this and say 19, and I produce T19. So now that I have my raw timestamps converted to strings, I would like to be able to discern which timestamps have an hour that I'm looking for and which timestamps do not. And we can do that with regular expressions. So count at hour will be a function that takes an integer and returns an integer count of all of the earthquakes that happen at that hour. So count at hour will take an hour, and we'll get the length of all of the data that matches this regular expression. We're going to filter anything that matches a regular expression defined by the return of the print statement. T $0 to D, and we'll pass in our hour and make sure that is a string, and then we will pass in our timestamps. Good. So let's demonstrate how this works. So count at hour 0. There were 76 earthquakes that happened at the 0 hour. There were 55 at hour 1. There were 52 at hour 2. And these will all be different based on your earthquake data set. So in my particular data set, I got 76, 55, and 52. If you didn't get the exact same numbers as me, don't worry. So now what I would like to do is to get all of the earthquakes by hour. And that is simply mapping count at hour to the range of numbers 0 to 23. And we now get the full breadth of the 24-hour period from 0 to 23. And now we can bring in the descriptive statistics functions to find the range and the standard deviation by hour. But hopefully you can see how this approach of using the regular expressions and the printf function, we have a lot of versatility over how we can find data in strings. It's time for our section review. So we began this section with installing the regular expression library, and we talked a little bit about the regular expression syntax. The dot matches any one character. The pipe allows us to match any expression to the left or the right of the pipe. We also talked about atoms, and atoms are expressions which are a single character, or the dot, or are grouped with parentheses, or are character classes, and they can be modified, and there are 4 common modifiers. The question mark matches 0 to 1 characters, the asterisk matches 0 to many characters, the plus sign matches 1 to many characters, and then there's the custom range, N to M, which matches N to M characters. One thing you should always be aware of when crafting regular expressions is that anytime you modify an atom with a minimum of 0, it will always match as true. We also talked about character classes at length. We used regular expressions within a CSV file and a SQLite 3 database. I'm going to put one important caveat to regular expressions at the end of this section. You should always thoroughly test your regular expressions. They tend to be difficult to debug. With that, let's introduce the next section. We will be discussing data visualizations. So section 4 is all about visualizations. In this section, we're going to be taking a look at installing the GNUplot command line tool and the EasyPlot library. And we're going to be plotting our first visualization. We're going to be customizing that visualization to make it publication ready. And we're going to add multiple plots to a single visualization. Along the way, we're going to be discussing the importance of the moving average, and we're going to be discussing the importance of feature rescaling. Video 4.1 in this series will focus on an introduction to EasyPlot. So we're going to be installing the GNUplot command line tool and the EasyPlot Haskell library. EasyPlot is just a Haskell wrapper for GNUplot. It allows us to interact with the GNU plotting utility from within Haskell and our IHaskell environment. We need data, and for that we're going to be pulling data from Yahoo Finance. I like Yahoo Finance because I can obtain the full history of any publicly traded company. And in this video we're going to end with our first plot. Let me move over to my virtual machine. So I'm in my virtual machine and we need to install GNUplot. The command for this is apt-get install GNUplot. Let's do a cabal update and then cabal install EasyPlot. Great. If you didn't get any error messages, that means you're ready to go. Now we need data. And as I said earlier, I would like to use financial data from publicly traded companies on the New York Stock Exchange. For that, we're going to go to Yahoo Finance. Now, the first company that I would like to look at is the Apple Corporation. And you have to know the symbol for all the corporations in order to use Yahoo Finance. And so the symbol for Apple is AAPL. So type in AAPL into the search box up here. And the first option is Apple. From here you can look at lots of information about the Apple stock, but what I'm interested in is historical data. So let's scroll down until we find the link for historical data. Right here. So I'm going to click on historical data. Once the page reloads, you're going to see 1-year historical data for the stock. You can see the date on which I am recording this video, and I am going to change the start and end dates for this range to be a date that exists well before the creation of the company. So I'm going to say January 1st, 1960, well before the creation of the Apple company. For the end date, I'm going to select today's date. I'm going to hit apply, and then I have to hit apply again. And now whenever I scroll down, you should see a link for download data. I'm going to click download data, and we see that we have the ability to download a CSV file called table.csv. Let's go ahead and download that file. Now, I don't like the file name that Yahoo provides, so the first thing I do is I make sure that I have my file in my download folder. You can see table.csv. I like to rename that file to be whatever the symbol is of the company I'm looking at. So move table.csv to aapl.csv. Let's take a look at that file. So this is the CSV file for the Apple company. You'll see that the CSV file has a header line as well as several columns of information, including the date, the volume, and the adjusted close. Now, the date column is a text field. The volume column right there is an integer field, and everything else is a floating point field. You should also notice that this file is in reverse chronological order. That means the most recent date in the file is first, and the very last entry in the file, it looks like December 12th, 1980. The last record in this file is the first day of trading. And we see that the adjusted trade value on December 12th, 1980 was 43 cents. The most recent adjusted close for Apple was $98.83. What I would like for you to do is to pause this video and to convert this file to a SQLite 3 database. Also, I would like for you to find 2 other companies on Yahoo Finance and repeat this process so that you create a database containing 3 companies and their entire histories. I have already done this prior to this video in order to save a little time, and I have created a database containing Apple, Google, and Microsoft. So I'm going to go over to my Haskell Data Analysis tab. I have created a database called stocks.sqlite 3. I will provide this file along with the files for this video, and it's already in my data folder. So I would like to begin with an analysis of that data set. So I'm going to go back into my analysis folder. We're going to create a new Haskell notebook. We'll call this stock analysis. Let's import a few libraries. So import graphics.easyplot, import database.hdbc, and import database.hdbc.sqlite 3. So 2 of those imports we've seen from our discussion on the SQLite 3 database. The first import, EasyPlot, is the one that we are introducing in this section. Let's make a connection to our database. Great. Now what I would like to do is to do our first plot of the Apple adjusted close. So let's pull out the raw adjusted close data for Apple. I'm going to call this AAPL raw. Going to ask our database for all of the adjusted close. I named my column ADJ close in my Apple table. And now I need to convert this data to the double type. You can see that AAPL raw is a 2-dimensional array of SQL values, and we need to convert this to a single-dimensional array of the double type. So let's do that. AAPL raw, we're going to map from SQL head. It's only going to be a 2-dimensional array with 1 column. So we can just call head on that 1 column to get the value. We'll convert that to a double type. Good. And let's look at those values. So we're going to plot. This is a new command, plot. And X11 means that we're going to plot directly to the X11 Windows environment. And plot requires that we have 2 coordinates, X values and Y values. Plot requires that we have a list of tuples, where each tuple consists of an X value and a Y value. So we're going to zip together our X values, and our X values are simply going to be 0, -1, onto infinity. And those will be our X values. And the reason why we're doing negative values is because our data set is in reverse chronological order. And then our Y values are going to be those adjusted close data. So it's going to take a moment to think about this, and we see our first plot. You'll notice a few things. This is not a true line plot. This is a scatter plot with lots of plus signs for all of our data points. For most of Apple's history, going back 9,000 trading days, the adjusted close has been less than $20. And it's only been within the last, say, 3,000 trading days that we've seen an increase in the adjusted close share price. So in our next few videos, we're going to talk about how we can clean this image up, make it publication ready. We're going to be talking about moving averages, and we're going to be talking about feature rescaling. Our next video is going to be all about the moving average. We're going to be expanding on our knowledge of the average by introducing the moving average. The moving average is simply the average of a subset of the data, where we have a small window in which we compute the average, and then we move that window, and then we compute the average again. And we keep repeating this until we've expended our data. So in this video, we're going to take a look at creating line plots. We're going to introduce the moving average, and then we're going to plot a moving average. Let me move back over to my virtual machine. Now, I'm right here where we left off in stock analysis, and I'm going to plot the last plot that we did in the last video. Now you can see the default marker type in this video. It's a lot of plus signs, and that doesn't make for an elegant graph. So what we're going to do is we're going to introduce the line plot. So plot x11 data 2D. Now data 2D is the formal way of introducing data to plot. Now there is the default, which we used in the last video, but this is the formal way where it allows us a little more customization. After you say data 2D, you pass in parameters. The first is a list of options, and we can say in those options that we want style lines. There is a second set of options, which you can include after that. We're going to leave that as a blank list. And then finally, we put in our data. So zip 0, -1, and then AAPL. Great. And that should produce our line plot. So here's our line plot using a continuous line from start to end. Notice how jagged it is. That's because this is a real-world data set, and real-world data set is frequently messy. So this is part of why we're introducing a moving average. I want you to take a mental note while you're watching this video and just note how jagged this data set is. What we're going to do now is introduce the moving average. So moving averages are used frequently in the analysis of a stock. For example, it's common for investors to compare a company's 50-day moving average to the 200-day moving average. Now, this is not a video on investing, so we're not going to get into the details of interpreting 50 and 200-day moving averages. You can research those on your own. But we're going to demonstrate here how to compute, say, a 200-day moving average. Now, these are called 200-day MAs, and the MA stands for moving average. So the first function which we are introducing is known as the moving sum. Moving sum is going to compute a list of sums based on the size of a window. And the size of the window is determined by the length of the first list passed to it. You'll see here that there are two parameters being passed to the function, a list of doubles and a list of doubles. The first list represents the window which we are trying to sum. The second list, right there, represents the rest of the data set. Now, if there is no rest of the data set in our first pattern, well then we're just going to return a list containing the sum of the first list. But let's say that there is data in both lists. Well, you'll see that in the first list, I shave the first value off the first list, and then I compute the sum where I immediately reattach that value onto the list. But then I recursively call moving sum again, where I take that first list where the first value has been shaved off, and then I add to the end the first value of the second list. And then I pass the shorter version of the second list as the second parameter. As you can see, the size of the first list always stays the same. So if the size of the first list is 3 in length, then at the end of the list it will still be 3 in length. So let's do a quick example of how this works. If I wish to compute the moving sum of the values 1 to 10, but I have a window size of 3, well then I need to set my first parameter to be 1, 2, 3. So here we have the moving sums of 1 to 10 with a moving sum size of 3. So as you can see here, we have the moving sum of the values from 1 to 10, but with a window size of 3. So the sum of 1, 2, and 3 is 6, 2, 3, and 4 is 9, 3, 4, and 5 is 12, 4, 5, and 6 is 15, and so forth all the way to the end of the list. Now our next function is the moving average function, and you can see it's longer than our moving sum, but most of this is error checking and looking for data which we should be catching. So this function is going to take two parameters, our data set, and then the size of the window that we want. And then it's going to pass that information on to moving sum, figure out the moving sums, and then simply divide by the window size for that particular data set. So I can say moving average, I can say my values from 1 to 10 with a window size of 3, and it's going to compute the moving average of this data set. So you can see that 6 divided by 3 is 2. 9 divided by 3 is 3. 27 divided by 3 is 9. And that's all we're doing. If I wish to compute the moving average of our Apple data, I can say Apple MA, and I can say moving average Apple. And if I want a 200-day moving average, I can just say 200. And I can now plot that data set. Plot X11. I'm going to say data 2D, style lines. There's our second list, and then zip. There we go. Now I told you at the beginning of this video to make a mental note about how jagged the original data set is. Well, take a note of this particular data set and how smooth it is by comparison. Moving averages will smooth a data set. It will take the noise and kind of cover it up. It'll still retain most of the shape of the original data set, but as you can see, a lot of the noise has been removed. In our next video, we're going to talk about how we can get publication-ready graphs. Creating plots that are publication-ready is essential simply because we must be able to share our knowledge. In this video, we're going to take a look at plotting multiple variables on a single plot, adding a legend to that plot, and then saving our plots to a file. So let me move back over to my virtual machine. And here I have the last plot which we created in our last video series, which was the 200-day moving average of the stock price of Apple since the beginning. I want to point out a few things about this plot. First, I have a legend up here in the top that just says plot1.dat. And if you've never seen this before, well, that doesn't really mean anything to anyone. Also, there's not a way in this mechanism to save this to a file. Oh, I suppose I could get some screenshot software and then create my own screenshot of this image, but that'd be a little bit of extra work. I would like to introduce further customizations of this plot, and I would like to save this plot to a file. And that's what I hope to do today. There are two variables in this notebook that I would like to point out. One is AAPL that we created in video 1, and one is AAPLMA, which we created in the last video. I would like to plot these two data sets on the same image. And to do that, we're going to plot X11, and then we're going to introduce a list, where each item in that list is going to be a data 2D. So style lines, and then zip 0, -1, AAPL. And then our second entry is going to be nearly the same as the first, but I'm just going to put MA at the end. So that's what our command is going to look like. You'll see that we now have two plots on this particular line. The red line is the first one, the green line is the second one, but we have both our original and our moving average plotted on the same plot. And that's nice. Take a moment and notice how little information is presented from about -3,000 to -9,000. It's almost a straight line. I mean, there's a little bump there at 4,000, but the most interesting parts of the data are within the last 2,000 trading days. So let's take a moment and plot just the last 2,000 trading days. So I'm going to take my line, and we're going to be building on this line throughout this video. Here is our data set, and I am going to say take 2,000. And once again, take 2,000. And this is going to plot just the last 2,000 trading days. All right. So take a moment and examine that green line. Notice anything funny about it? It's supposed to be a moving average, but if it were a true moving average, shouldn't it follow the red line more closely? It looks like it's lagging behind the red line a little bit. That's because the moving average is always computing the previous 200 data points. We would really like to center that moving average over the point where it spreads 100 units in either direction. So we can make a quick change to our plot. where we simply reset the starting point of the moving average to be 100 points behind. So we'll say negative 100 there, and negative 101 there. And we're starting at negative 100 simply because 100 is half of 200. All right, now take a moment and look at this much better moving average, where the green line now delicately hugs that red line. I think it's a much better visualization. Now imagine that you're seeing this image for the first time. You don't have the benefit of hearing our dialogue about the previous videos about what these lines mean. And there is a legend in this plot, but it just says plot1.dat and plot2.dat, and those aren't helpful at all. What we need to do now is introduce titles to each of these plots. So I'm going to copy my data set again, paste it here. Now in the options after styles, we have the option of creating a title, where I can say AAPL adjusted close. Here I can say title AAPL 200 day MA for moving average. Great. Now you can quickly identify a line based on its color, and you can see which color is associated with each data set. This is important for the sharing of our knowledge. Let's say that we don't like the colors of our plot. Our defaults are red and green, and that's great for most cases, but let's change this to say blue and black. Well, we can take our plot again and say, after our title, I can say color blue for our original data set and color black. Now if you go through the EasyPlot documentation, you're going to see lots of colors that can be defined for our plots. But with that little extra, we can perform a little more customization to our plots. Finally, I would like to save this plot. To do that, we need to change how the image is directed, and that involves changing that X11 right there. So once again, I am going to copy and paste my plot. I believe I'm happy with it. I'm ready to drop it into a publication and present it to the world. And I am going to change this to PNG, so we'll be saving this as a PNG file. We'll say this is the adjusted close with 200 day MA.png. Great. Now it doesn't display anything on the screen, it simply writes that to a file in our local directory. I'm going to go over to my terminal and see if I can find my file. So I'm in my analysis folder, and I'm going to use IceWeasel to look at my file. Great. I can now drop that image into a publication, say a Word document or a LaTeX document, and it should be sufficient. Now, one thing that EasyPlot won't do is that it won't add titles and it won't add axis lines. So what I recommend you do is you add that information into the legend details. Our next video will be on feature rescaling. In our last video, we explored the essential features of EasyPlot towards getting our images publication ready. In this video, we're going to explore how to plot multiple companies onto a single plot to accurately reflect their growth. So the question I would like to answer in this video is, over the past year, which of these three companies, Apple, Google, or Microsoft, has had the highest percentage of growth in their stock value? In this video, we're going to take a look at trimming our data set to 252 days. Why 252? Well, there are 365 days in a year. If you cut out the weekends, and if you cut out the United States federal holidays in which the New York Stock Exchange doesn't operate, you're left with 252 days. So 252 is our magic number to represent 1 year of trading data. We're going to introduce feature scaling, and we're going to plot our three companies that have been feature scaled. So here's the formula for feature scaling. It is simply a value minus the first value in our data set divided by the difference between the largest and smallest values. It's a fairly simple formula, and what this formula does is that it will take any data set and rescale it so that it's on the range of -1 to 1. What's also nice about feature scaling is that this formula won't change the shape of your data at all. The shape remains the same. Now let's go over to our virtual machine. We are back in our virtual machine, and what I would like to do is to fetch out of our database the Microsoft and Google datasets. I mentioned in video 1 of this particular section that I would like for you to build a database of 3 different companies, and I hope you have that dataset ready. If not, I hope you're willing to grab the dataset that accompanies these videos so that you can follow along. Now here I have the lines ready to go in order to pull our Google and Microsoft datasets. Google's stock symbol is known as GOOGL, and so I have named my table GOOGL. And Microsoft's stock symbol is MSFT. Therefore, I have named my table MSFT. What we need to do next is to trim our datasets to the most recent 252 trading days. So AAPL 252. I'm going to call all of these datasets by their symbol and then the number 252. So take 252 from AAPL, MSFT 252, and GOOGL 252. Good. Next, I would like to plot these datasets so that you can get an idea of what they look like in their original shape and scale. Now in my clipboard, I have the line ready to go where we can plot our 3 datasets. The first dataset will be Apple, the second will be Microsoft, and the third will be Google. And it'll just be the most recent 252 trading days. All right. So each of these 3 companies trades at a particular dollar value, but each of them trade at a different dollar value that doesn't relate to any of the other companies. And this is true for any stock that's publicly traded on the stock market. If you know the price of a company, that really doesn't tell you anything about if that company is doing well or not. We would like to feature scale these 3 companies so that they all exist on the same plot, and they all exist at the same scale. So let's introduce our feature scale function. So our feature scale function is going to be called rescale. It is an implementation of the formula that I showed you in the slides just a little bit earlier. And it takes one data set and it returns a data set of equal length. And as you will see, the shape of these data sets will remain the same, but the scale of the data sets will be on the range of -1 to 1. So I'm going to do a rescale here for each of our 3 data sets in our plot line. And here is our plot. Now notice, because every data point is first subtracted by the very first element for all 3 lists should be 0. And you can see that that's true in this particular plot. So this is the feature scale plot for all 3 of our data sets. We can tell that the green line corresponds to the company that has grown the most, the blue line corresponds to the company that has grown the second most, and the red line corresponds to the company that has grown the least. And in order, it looks like green line is Microsoft, the blue line is Google, and the red line is Apple. So over the past year, Microsoft has done the best, Apple has done the least. We can also tell from this particular plot that Microsoft and Google have increased in value over the past year, where Apple appears to have decreased in value over the past year. Feature scaling allows us to take any companies and plot them on the same chart, and allows us to accurately compare the values of those companies without losing the original shape of the lines produced by their values. In our next video, we will cover scatter plots. The financial data that we've used up to this point in this section is usually considered time series data. Time series data is simply sequential data that usually includes a date or a timestamp. Scatter plots don't have to be tied to sequential data. So in this video, what I would like to do is try to develop an understanding of the share price of a stock and how much that stock is traded in terms of volume. So we're going to be comparing the stock price to the volume traded with a relatively simple plot. You're going to see very quickly that this plot is insufficient to meet our needs of understanding the plot. So we're going to be comparing that stock price with a log of the volume traded. Now what I would like to do to end the video is to perform this analysis on Apple, Google, and Microsoft. I am back in my virtual machine. I'm looking at my stock analysis. We already have the adjusted close values for Apple, Microsoft, and Google. And what we need now is simply to get the raw data for the volume. I already have it here in my clipboard in order to get that code ready. We are pulling the volume data out of our database in much the same way as we pulled the adjusted close. So let's go ahead and run that one. So my adjusted close values are all the symbol itself for the three respective companies, whereas the volume is going to be the symbol plus the word VOL, as you can see in these last three lines. Great. Let's plot that adjusted close. So we're going to be comparing AAPL with AAPL's volume. Now, what you're looking at here is all along the x-axis, we have the share price of the company, and along the y-axis, which stretches into the, I believe that's the billions, into the billions, we have the volume traded. And you can see that there's a huge shift on the left side of the graph. There's lots and lots of data points, whereas on the right side of the graph, there's not much. And we have one lone dot way up here that is extending our plot. Now, this doesn't give you a good idea about the shape of the data. Now, in order to solve this, what we can do is we can compress the data near the top while doing relatively little to the data at the bottom. There's a simple math expression for this, and that is you simply take the log of the plot. Now let's go ahead and apply the log to our volume data. Grab our line here. We're going to say map log volume. All right. Now, taking a log of the volume data does change the shape. Unlike our past videos where we tried to retain the shape of the data, taking the log of the plot loses a lot of that shape of the data. But this also allows us to focus in on those lower values. So here you can see an obvious trend line that's downward, so that as the stock price increases, the volume traded decreases. Now, before the stock price of 20, or maybe even 10, it doesn't seem to even really matter. But after 10, you can see a noticeable drop that seems to have a pattern to it. Now, this is just for Apple's stock price. What I would like to do is see if this holds up true for our other companies. Now what I would like to do is to plot all three of our companies with a log plot. So this is not going to be an accurate reflection of the three companies combined because, as we said, the log plot does change the shape of the data. What I would mostly like for you to do whenever I run this plot is for you to examine the trends of each of the three companies. Notice that all we're doing is we're taking a log of the volume for the respective companies. All right. So here we have in red the original Apple dataset, which you saw earlier. In green, we have the Microsoft dataset. And in blue, we have the Google dataset. And you'll notice all three datasets have that downward trend. We wouldn't have been able to see that downward trend without taking a log of the data. So why do we see this downward trend? Well, there's a relatively simple explanation. As companies increase in value, our purchasing power decreases, and we can buy fewer shares. We're highlighting the advantages to the adage of buy low, sell high. There's not a lot of predictive analytic power to this particular visualization, but I still believe that there's an educational value to it. It's time for our section summary. So we began this section with installing the GNU plot and the EasyPlot Haskell library. We discussed the moving average, and analysts like to use the 200-day and the 50-day moving average frequently in market analysis. But beware, these are not substitutions for good solid research. We discussed how to make our plots publication ready by adding a legend and saving our images to files. And we discussed how to feature scale our plot so that's on the range of -1 to 1. Feature scaling always retains the shape of the data. Finally, we demonstrated the utility of taking the log of data. That allows us to compress higher values while retaining the general shape of lower values. Now this does change the overall shape of a plot. In our next video, we are going to be discussing the normal distribution. Section 5 is on the topic of kernel density estimation. Because kernel density estimation is a rather involved operation, we're going to split this up over several sections, so hopefully it's easier to digest. In video 1, we're going to introduce the central limit theorem and the normal distribution. In video 2, we're going to introduce the kernel density estimator. In video 3, we're going to apply that kernel density estimator. So we're going to start off with the normal distribution. The normal distribution is an important formula for the study of even basic statistics and data science. Data science at its heart is mathematical. We're transitioning away from the technical aspects of Haskell and file formats. So in this video, we'll be discussing the central limit theorem, which is essential to understanding the normal distribution. We'll then be introducing that normal distribution, and then we're going to be exploring the parameters of the normal distribution. So here is the definition of the central limit theorem. The central limit theorem states that, given certain conditions, the arithmetic mean of a sufficiently large number of iterates of independent random variables, each with a well-defined finite expected value and variance, will be approximately normally distributed, regardless of the underlying distribution. Now I realize that's a mouthful, but let's see if I can convert this definition into some plain English. So imagine that you have a large data source, and we've worked with several data sets that are sufficiently large. Calculate the mean and the standard deviation. If you can't, this won't work. We're going to split that data into smaller chunks. We're going to take the averages of each of those smaller chunks. We're going to count how many times we see each average, and then we're going to plot that information. Once you get that plot, you'll always get something that looks like a normal distribution. And this happens regardless of whatever your original data source is. Now let me go over to my virtual machine, and I have my Jupyter notebook ready to go. I have a notebook titled Normal, and I have a few imports ready to go. The one import that we're using here that you may not be familiar with is system.random, and that is for generating random numbers. So to begin, we need to create our random number generator. And this is what we're going to use in order to demonstrate the random number generator. What I would like to do now is to generate 100,000 values on the range of 1 to 100. So there is a function called randomRs that generates an infinite stream of random number variables. And we're going to take the first 100,000 from that list. So randomRs, which generates our random stream on our range from 1 to 100, we have to pass in that random number generator that we defined earlier. And we're going to specify that these values are all going to be double. Let's look at the first 10 values in our list. And you can see that they're all double. They have long floating point portions. Here are the first 10 values. What we need to do now is to divide this data set up into chunks. And what I would like to do is to generate 10,000 chunks, each of size 10. So let's create our quick function. It'll be called chunk, and if it takes an empty list, it'll just return an empty list. But if it sees a list with data in it, it's going to take the first 10 items of that list and then recursively call itself by dropping those first 10 items and passing the remainder. So this is going to generate our list where each sublist will be 10 elements long. And let's check out the length of chunk values. All right, we have 10,000, which is what we were expecting. 10,000 times 10 is 100,000, our original value. Next, I said that we need to compute the average of each of these chunks. So AVGS is equal to map, and we're going to take the average of each of these sublists. Right, so there, we have taken the average of each of these sublists. Good. I said that we need to record how often we notice each average. So I'm going to cheat a little bit, only a little, and I'm going to round this information to the nearest integer. We then sort those list of values and perform run length encoding, which we generated back in section 1. So pairs is going to be equal to run length encoding, and we're going to pass in our sorted map where we round each of our averages. All right, time to plot. So I'm going to plot, we're going to plot to the screen, data 2D, style lines. We're going to map our values over this quick little function. You're going to see why we do this in a little bit. Because our run length encoding algorithm produces a integral value for each of the first values in our list, the plot function doesn't know how to plot that. So we have to convert from integral. So from integral on our x, and then we pass in our y, and then we pass in our pairs. Because this is a randomly generated data set, I don't know what's going to be displayed. All right. Now, according to the central limit theorem, whatever is displayed should be approximately a normal distribution. And the characteristics of a normal distribution are that it has a high center in the middle and extends downward pretty evenly on both sides. And so here we have that approximated normal distribution. Now, this is the approximated normal distribution. You can see it's jagged because our data is random and not perfect. What I would like to do now is to introduce the actual normal distribution. So here's the normal distribution. I realize this formula is intense if you've never seen it before, but focus in on the parameter side instead of the actual formula side. So there's only three parameters, x, mu, and sigma. X is the dataset which represents the domain. Mu represents the mean, where we want the mean of our dataset to be. And sigma represents the standard deviation, or how thin or wide we want our dataset to be. Now, because this is a hairy formula, I've already implemented this, and I'm going to paste it into our window. So here's our quick function for the normal distribution, and you can see the three parameters here. We have mu, which represents the mean, SD, which represents the standard deviation, and x, which is the domain over which we are mapping. Now, here's what you need to remember about the two parameters. The two key parameters, mu and standard deviation. Mu represents the center line location. Positive means it will exist to the right of 0. Negative means it will exist to the left of 0. The standard deviation represents the width. High numbers in the standard deviation represent wide plots that are low, and low numbers in standard deviation represent high plots which are thin and narrow. So let's go ahead and plot our normal distribution. We need to plot over the domain, and I prefer to plot on the domain of -5 in 1/10 increments. Now let's plot our values. So we're going to do a data 2D, and we're going to do style lines, and we're going to zip our domain, and we're going to map that domain over the normal distribution. I'm going to specify a mean of 0 and a standard deviation of 1. Then we're going to map our domain over that normal formula. So what you see here is the true normal distribution. You can see that the peak of the normal distribution is at 0.4, and the width of the normal distribution extends just past -3 on the left and 3 on the right. Take a mental note of those values. We're over 0, our peak is at 0.4, and our widths are at -3 and 3. We're going to come back to those values. I would like to continue to demonstrate how the standard deviation affects these parameters. So if I change this to 5, large standard deviations produce wide plots that are low. The peak of our standard deviation is still over 0 because our mean is at 0, but now it's only at 0.08. Our widths extend well beyond the 5s, -5 and 5. So this is a much wider plot that's lower. If I perform this again, we're going to change this to 0.5. See, once again, we're over the 0, and we have a much narrower plot that only exists from between -2 and -1, and on the other side, 1 and 2. And the peak of our plot is now at 0.8, so it's much higher than our original. All right, so now you've seen how the standard deviation affects the plot. Let's see how the mean affects the plot. So I'm going to go back to my original with a standard deviation of 1 and a mean of 0, and I'm going to change this mean just 2. So whenever you have two standard deviations which are the same, the shape of the data will be identical, just the mean offset will be different. So before we had a mean of 0, and the center of the plot was over 0, and now we have a mean of 2, and the center of the plot is over 2. Everything else about the plot is the same. The width is the same, and the height at 0.4 is the same. So now that you have a little bit of a background on the central limit theorem and the normal distribution, and the two key parameters of the normal distribution, the mean and the standard deviation, I feel like we're ready to go to talk about kernel density estimation. So our next video will be about how to implement the kernel density estimator. Kernel density estimation is a process by which we can estimate the shape of a data set. After we have computed the shape of a data set, we can compute the probability in which an event will happen. So in this video, we're going to introduce the kernel density estimator. The kernel density estimator requires a kernel function, and we are going to discuss the requirements of a kernel function and how the normal distribution meets those requirements. Finally, we're going to compute the KDE of a set of values. So kernel density estimation tries to estimate the shape of a data set. All data has a shape. You could also refer to this as the density, and that shape is not always clear. Once we have estimated the shape of a data set, we can compute the probability of a particular observation. We require a kernel function, and in this video we will use the normal. There are three requirements of a kernel. There are several different types of formulas that meet these requirements. First of which is that a kernel needs to be smooth. A kernel needs to be symmetrical and non-negative. Symmetrical means that for a given position that is negative, you have the exact same value for the same position when it is positive. Non-negative simply means that the line exists at or above 0. And then finally, the area under the curve is 1. So here we have the formula for the normal distribution expressed as an integral from negative infinity to infinity, and that this result should be 1. And what's nice about the normal distribution is that it doesn't matter what you set as the mean or as the standard deviation, the result will always be 1. So here's the general algorithm for kernel density estimation. For each value in our dataset, we're going to compute a normal curve with a mean of that value. So the curve itself is going to shift around. We're going to take all of those curves and we're going to add them together. And then finally, we're going to plot. So let's go over to our virtual machine, and we're going to take a small set of values, only 3. I'm going to call this values, and we're going to say 115 is our data set. So let's imagine that we have a data set. We're trying to understand the shape of this data set, but we only have these 3 values to work with. Now we could take the range of these values, and by looking at it, you can tell the range is 1 to 5. Now whenever I compute a kernel density estimation, I need to set a domain. And I like to pick my domain to be whatever is 5 minus the lowest all the way up to 5 greater than the highest. So we need to set a domain of -4 to -3.9 all the way up to 10. So that is a fairly broad domain. I think this produces nice plots. Our next step is to compute the normal of each of our data sets. So curve 1 will be the normal at mean 1, because 1 is in our data set. And I like to keep the standard deviation at 1. Curve 2 will be our normal at position 5, because that's another one of our values. Again, I keep the standard deviation at 1. So for each value in our data set, we compute a normal, where the mean of the normal is at that value's position. So let's go ahead and create a list of all of our curves. And this will be curve 1 again, and curve 2. Now we need to compute the kernel density estimation, and there we just add up all the curves together. So I'm going to call this the KDE, where we use the tool fold L1. It's a nice little Haskell power tool for combining lists. And we are going to use zip width with a plus over our list of curves, and that adds up all of our curve data together. Now, let's go ahead and plot this information to see what it looks like. So, data 2D, style lines, and then we are going to blank list, and then we're going to zip our domain with our KDE. Alright, so there is the shape of our data set. Now don't try to read too much into the y-axis at this point. Just try to notice that at about position 1 we have a very high likelihood, and at position 5 we have another high likelihood. There is a dip at position 3, which is midway between 1 and 5, and that the graph tends to trail off in both directions on either side. So this is the shape of our 115 data set. Now, what I like to do is I like to make the area under this curve equal to 1. And we can do that. I'm going to call this KDE adjusted, so ADJ, by simply dividing by the sum of the data set. So sum KDE, KDE. Good. Now if I compute the sum of KDE adjusted, I get a value that's almost 1. Now I'm going to take my plot line here, and I'm going to change this to KDE adjusted. Now this won't change the shape of my data set, but it does now introduce probabilities for events. For example, now, if we assume that we have a continuous data set, the probability that I will get exactly 1 is a little over 2.5%. And the probability that I'll see a 5 looks like it's a little less than 1.5%. And the probability that I'll get a 3 is about 0.5%. So notice that the graph is continuous and that we are allowed to see the probability of every point along the shape of our data set, not just at the integer portions. Great. We now have enough to introduce the KDE function, which I will introduce at the beginning of the next video. In our next video, we're going to introduce an application of the kernel density estimator, along with the kernel density estimator function. This video will serve as our real-world application of the kernel density estimator. So in this video, we're going to take a look at the Monet dataset. Monet is a famous French impressionist, and many of his paintings have sold at auction for millions of dollars. And the Monet dataset is a record of all of those final auction prices for his paintings. We'll be discussing the parts of the kernel density estimator function, and then we will be answering a question using the kernel density estimator. What is the probability that in the future a Monet painting will sell for $5 million or more? So I'm back in my virtual machine. Let's do a Google search for Monet paintings. Yay. So this is my excuse for putting beautiful Monet paintings into my videos, and we're going to be discussing the auction prices of these paintings. Aren't those lovely? Hopefully you recognize a few of those. I'm going to go back over to my All tab and type in dataset. So I'm looking for the link Economic Analysis 7th edition datasets. So these appear to be datasets that accompany an economics textbook. Let's scroll down, and I want to look for the option for Monet datasets. Oh, I believe I already passed it. It's near the top. Ah, there it is. It's table 4.1. There are several columns in this particular data set. We're only interested in the first one, and that is price, sale price in millions. We're going to download that data set. I have table f4-1.csv. Let's rename that table to Monet and discuss the data set itself. Alright, so here we have the data set. There is a header line. We're only worried about the price, and there's something I want to point out. Some of these prices, if it's less than $1 million, you'll notice that there's no leading zero on this value, and it appears throughout the data set. So I'm going to introduce a quick fix. First, I'm going to remove that header line. There it goes. I'm going to save the file and get out of VI. And let's do a quick sed script. So sed-I, that means we're going to do an in-place change on the file. And anytime we see a line beginning with an expression of a dot, we are going to replace it with a 0 dot. Forgot my inline. There we go. And now whenever I go into my file, all of those values that had just a dot at the beginning now have a 0 dot at the beginning. Now let's go ahead and copy this file into our data folder. Great. Now I want to go back to our normal notebook, and I need to play with the imports a little bit. I need to load our CSV library, and I need to add several imports. I need to add import data.maybe. I need to import my CSV, and I need to import text.csv. And that should do the trick. Now, in order to save us a little bit of time, I'm going to scroll down to where I have defined the normal in my notebook. It should be there. I'm going to rerun that line just to make sure it's still there. Now let's introduce the KDE function. Now, this is going to be a review of the last video. We're only passing in one data set, and we are returning a maybe of two bullet values, the first of which is the domain and the second of which is the range. And the range represents the adjusted KDE. As you recall from the last video, we are setting our low value to be whatever the low is -5, and the high value to be whatever the high is of our domain +5. And then we just follow the steps of the KDE as we did them, concluding with the shape of the KDE divided by the sum. Good. Let's go ahead and grab our data from the Monet data set. Okay. And now we need to read those Monet prices. Now, hopefully you did the sed trick where we added zeros to the beginning of some of those line items. If you didn't do that, then this next step isn't going to work. So we're going to get our Monet prices, and we're going to read the index from Monet from column 0. We're going to parse these as a list of doubles. Great. Without doing anything to this data set, let's take a moment and plot what this data set looks like. So I'm just going to plot the values starting from 1, and we're going to sort the Monet prices. So you get a quick idea what are the smallest values and what are the largest values. So you can see here that we have over 400 observations, and the y-axis here is the value in millions. Some of these get to over $30 million, but as you can see, most of them are below 5 million. It looks like the 5 millions end at about, I say, after 370 or so paintings are less than 5 million, and the rest are above 5 million. Okay. Kind of gives you an idea about the data set distribution. But this doesn't describe the shape of the distribution. The KDE does that. So let's compute that KDE now. So just domain and then the KDE adjusted. Great, there we go. Let's go ahead and plot this. So plot x11 zip domain KDE adjusted. So here is the actual shape of the data. You can see that there is a strong peak in the data set just after 0. Now here the x-axis is shifted. We now have the x-axis representing a dollar amount in millions. And so here's 35 million, here's 5 million, here's -5 million. Right at 0, you see how our continuous function is predicting sale prices of Monet paintings that are negative. You can essentially just cut those off at 0. But our question that we set forth at the beginning of this video is, what is the probability that a painting will sell for 5 million or more? So what we do is we figure out all of the domain values that are 5 or greater, and then figure out what the corresponding probabilities are, and then add those probabilities together. So let's find those indices in which the price of the painting is 5 or greater. find indices. This is a wonderful little function in the data.list library. We're going to say greater than or equal to 5, and then we're going to attach our domain to that. And then we map those to the adjusted KDE and then compute the sum of that. So sum of our map. We're going to pass in a function to map where we just say the KDE adjusted whatever that X index value is from our indices list. Great. And we see that we get a probability of almost 20%. It's almost 0.2. So if a Monet painting ever comes up for sale in the future, there is a 0.2 probability that it will go for 5 million or more. So hopefully that gives you an idea about the utility of the kernel density estimator. It's time for our section review. So in this section, we introduced the central limit theorem. We introduced the normal distribution. The normal distribution is a smooth, strongly peaked function where the area under the curve is 1. We discussed how the normal distribution works as an excellent kernel for the kernel density estimator. We performed the kernel density estimation on a small data set. That small data set was simply 115, and discussed how the shape of the data looked. And then we performed kernel density estimation for the Monet price data set. In our next video, it's going to be a section review where we accumulate all of the content that we've gone over in this entire course, and we're going to step through it in just a few videos. Section 6 will serve as our course review. In this section, we're going to tie together the first 5 sections using the Movie Lens dataset from the University of Minnesota. We're going to cover the highlights from all of the sections and hopefully drop in some new content along the way. So in this section, we're going to be taking a look at converting variations of CSV files into SQLite 3. We're going to be using SQLite 3 select queries and our descriptive stats module for descriptive statistics. We're going to be creating more compelling visualizations using the EasyPlot library. And then we're going to be trying to answer a few interesting questions by applying the kernel density estimator to our Movie Lens dataset. So video 6.1 is going to be discussing CSV variations to SQLite 3. CSV file stands for comma-separated values. And perhaps you heard me in section 1 about how CSV isn't really a standard. And it may come as a surprise to you that comma-separated values, the values do not have to be separated by commas in order to still be considered a CSV file. That's the lack of standardness there. So in this video, we're going to be downloading the Movie Lens dataset. We're going to be exploring the types of CSV file formats in this particular dataset. We're going to be using SQLite 3 in order to convert the dataset. So I'm back in my virtual machine. Please go to google.com and type in Movie Lens dataset. The dataset that we want is the 100K dataset, and I can find that by clicking on 100K or just clicking on the main link. Now there are several datasets in this file. Movie Lens is a project at the University of Minnesota in which researchers have asked people to rate movies on a scale of 1 to 5. 1, they don't like the movie. 5, they love the movie. So the first 100K dataset was released back in 1998. We're going to be working with this older dataset because it's the smallest. Let's download it. I'm back in my Downloads folder. Let's explore. I should have an ml-100K file, and I do. Let's unzip it. Let's enter the folder. There is a file in our folder called README. Let's open that up. I do encourage you to read this entire file. There are guidelines on how this dataset can be used. For example, you must download it from the Movie Lens site, and you must not use this dataset for commercial purposes. We're using it for academic reasons, so I feel like it's okay. So let's scroll down until we find the description of the file formats. Here are the brief descriptions of the data. Great. We're looking for u.data. That is our primary file. I'm going to open up a new terminal, and let's explore u.data. There are 100,000 ratings in this file, and you can see that there are 100,000 lines in the file. down here at the bottom of my window. So one line represents one record. It says that there are tabs separating the list of values, and there are 4 fields. So we can see that there are 4 fields and that they are all integers, and they represent the user ID, item ID, the rating, and the timestamp. So I'm going to create a new terminal over here. I now have 3 terminals going. Hopefully you can stay with me. So I'm going to be jumping back and forth between the 2 terminals in the lower portion of the screen. We're going to call this SQLite 3 movies.SQLite 3. Here's where we'll be creating the tables. Let's create a table for our data. So I'm just going to call this create table data. And now we need the fields. User ID, integer. Item ID, integer. Rating, integer. Timestamp, integer. Now, because this is a tab-separated value file, we need to use our mode tabs. In the past, we've used CSV. Well, there's a built-in mode just for tab-separated values, and it's called tabs. Now we need to import our data. Good. If all goes according to plan, you should now be able to run select queries from here on your data. So select everything from data, limit, let's limit 3. Good. We get the first 3 rows in our data set. So the first item should be 196.242.3. 196.242.3. Yeah, looks like we got it. Let's scroll down to the next file. User.info. We can look at user.info. There's only 3 lines in the file, and it just talks about the data set. It's not that interesting. We're going to skip it. The next one is u.item. So u.item includes information about the movies. See in parentheses there, but they call it items. So this is a tab-separated list of, and then it has all of the fields there. There are a lot of fields in this data set, 19 in total. Now you'll notice the documentation says tab up here, but if we look down at the file itself, there are pipes. Those aren't tabs, those are pipes. All right. So what I would like to do is to create a table for our items. Now, because this is going to be a really long line, I'm just going to paste it. All right. So create table items, and then I have a description there of all the fields. I will include this line because it's so long in the content that goes along with this video series, so you don't have to retype all that. But let's go. Because this is a pipe-separated file, there is no built-in pipe-separated mechanism. So we just have to declare that the separator is a pipe. Next, we say that the mode is a list. Now, whenever we set up list mode, it will look for the separator field and determine, oh, that's how we separate our file. So let's continue. Now we import u.item into items. If all goes according to plan, you should have your item set up. Select all from items, limit 2. Okay, we got Toy Story and we got GoldenEye. Let's continue looking at our files. Genre is just a listing of genres. It's not that interesting. User has the demographic information of all the users who the researchers interviewed. Let's explore that one. You'll see, again, it is another pipe-separated file, despite the fact that the documentation says it's tab. Again, we're going to create a table based on this content. Create table, users, user ID, it's user ID int, age int, gender string, occupation string, zip code int. All right, let's type that out. So age, text, gender, text. Misspell. Great. Now we already have our modes set up for pipe-separated values, so we should just be able to do an import. Import u.user users. And let's do a select query. So select from users, limit 3. Good. Occupation is a list of occupations. Again, not that interesting. The remaining files in this dataset are used for machine learning projects, and if you stick around for course 2, we'll be exploring those datasets. But for now, we're just going to stick with these 3 tables. All right. So we have our datasets set up, and I believe we're ready to go. In the next video, we're going to be using descriptive stats with SQLite 3. This video will serve as our review of the SQLite 3 select queries and our descriptive stats module. So in this video, we're going to take a look at loading data from our movie lens dataset into an IHaskell notebook. We're going to be demonstrating the built-in AVG function in SQLite 3. We're going to be demonstrating a simple inner table join in SQLite 3. And we're going to be using SQLite 3 and descriptive stats to find the highest median across 3 genres of movies. I want to know which genre is considered the highest rated: action, drama, or sci-fi movies. When we last left our video, we had just created the movies.sqlite 3 database. What we need to do is we need to copy that file into our data folder. Now if I look at this folder, I should see our movies.sqlite 3 file. Great, I do. So I've already created a movie lens notebook in my IHaskell environment. Here's where we're going to study the movie lens dataset. So let's begin by loading our descriptive stats model. Now let's import our essential libraries. So data.list, import database hdbc, import database hdbc.sqlite 3, and import descriptive stats. Next, we need to create a connection to our database. Now, if you've used databases for any length of time, you've probably already run into the AVG function for computing means. It's built into SQL, and let's go ahead and demonstrate that now. So if I do a quick query on our database, and I say select the average rating from our data set, we see that the average rating is 3.53, and that's across all movies. Now, while that's great, I'm going to copy and paste this. I change AVG to say something like median, which is another popular descriptive statistic. We see that median doesn't exist. Let's try again with another popular one, the mode. Again, it doesn't exist. It gives us an error. So this stresses the importance of having a descriptive stats library, such as the one we made in section 1. So let's create a data set consisting of all of the ratings for movies that are of the action genre. Now our genre information is in the items table, but our ratings is in the data table. So what we have to do is perform an inner join in order to align these two data sets. This is fairly straightforward to do using a little bit of SQLite 3 SQL query. So I'm going to call this ratings action. So we're going to query our database. We're going to do a select data.ratings. Now anytime I do a table join, I prefix all of my columns with the tables. So I do table.column. In this case, it's rating data.rating. We are pulling from data, and we're pulling from items. And I want to know any place where our data.itemID field matches our items.movieID field, and where the items.action field is equal to 1. Good. Let's check the length of that data set. Of the 100,000 ratings in our data set, it looks like over 25,000 ratings represent action movies. Let's create our read column partial function that we've used in past videos. So read column is a mapping from SQL. Okay. Now let's compute our mean. So the mean of, we're going to be reading the column information. We're going to do a head.transpose of our ratings of action movies. And we're going to parse that into a list of doubles. Okay. As we recall earlier, the overall average of our ratings is 3.53, but of just action movies, it's 3.48. All right. Let's try this again with the median. We change mean to median, and we see that the median is 4. Good. Let's do this again. Copy this, and we're going to come down here, and rather than action movies, let's say drama movies. So I can come down to the end of my query where I have action, and I can change this to drama. And now I can once again compute the mean of my drama movies. I see 3.69. Ah, that's good. And the median. Once again, it's 4. And then finally, we can do this again for sci-fi. And we can pull our items where sci-fi is equal to 1. Again, let's pull our mean of sci-fi movies. It is at 3.56. And once again, the median. Alright, so we've discovered that the median rating for all 3 genres that we decided to look at in this video was 4. And that of the means, they all had slightly different means. The highest mean was from the drama category, and then the sci-fi category, and then the action category. So, more users appreciate our dramas than our sci-fi or our action movies. Great. In our next video, we will be creating compelling visualizations of the movie lens dataset. I would like to propose a question. As we get older, do our perception of movies increase with approval, decrease with approval, or stay about the same? In other words, what I'm trying to figure out is, as we get older, do we appreciate movies more and rate them higher? Or do we appreciate movies less and rate them lower? Or do they stay about the same? What I would like to do is pull together the data in this video, plot it, and see if we can answer that. So in this video, we are going to perform a table join to study age and the average movie rating. We're going to be parsing that information into a usable type for plotting, and then we're going to plot. So I'm back in my Movie Lens IHaskell notebook, and I'm at the top of my notebook and with all my import statements. So here I'm going to add graphics.easyplot. It's our plotting library. Great. Let's scroll down. Because of how I stated the question, this can be done in a single select query. So let's get started. Age ratings is what I'm going to call my result. We're going to do a quick query where we select users.age and average data.rating. We're going to rely on the AVG function built into SQLite 3 for our averaging. We're going to be pulling from data and from users, where data.userID is equal to users.userID. At this point in our query, if we were to perform a cross-section of all of our user ages and data ratings, then every age would have a corresponding rating. And if we were to average that corresponding rating, we would just be averaging a single number. And so the averaging wouldn't really serve a purpose. What we need to do first is to group all of those ages together and then average that group in batch. So we can do that simply by adding group by to the end of our query. And we specify the column in which we wish to group, and that is users.age. Hopefully I typed that correctly. Great. Next, we need to parse the information out of our age ratings variable. So age is equal to read column, and we're going to read column on our age ratings. But before we can read the age ratings directly, we need to massage that data set a little bit. Right now, it is in a column format where the data we want is in columns. Now, you just can't ask for a column in this particular two-dimensional data structure. You can only ask for a full row. So what we can do is we can transpose the data and then ask for a full row. So we're going to pull from the first row after we transpose. So let me get an extra set of parentheses in here. Hopefully they line up. And we're going to parse this as a list of doubles. Good. Now in our age ratings table, the ratings, the average ratings, are going to be on the second column. And once again, you just can't grab a column. You have to transpose and pull from the second row. So all we do is we change that 0 to a 1 and change this to average rating. Great. Now we need to plot. So plot x11. We're going to zip our age and our average rating, and we have our plot. We can see a few features over here. For instance, the lowest point on the graph appears to be, I'm going to guess, 10-year-olds with an average rating of less than 3. And the highest rating appears to be up here. And if I hover my mouse pointer over that, it looks like 57-year-olds with an average rating of 4. There's another high point over here. It looks like 72-year-olds with nearly 4. So I submit to you that there is an upward slant to the data set. In other words, I believe, based on looking on this graph, that as we get older, we tend to appreciate movies more. Now, is there any truth to this? Well, we would have to perform something called regression analysis, which is a topic for another section. For now, we're just going to have to speculate based on the direction of the data. This visualization. We could improve this plot by adding a title, and so I think we should do that before ending the video. I'm going to grab this, and we're going to say data 2D, title, age versus average rating. Let's add our blank list there. And then, great. I believe this plot is publication ready. In our next video, we will discuss kernel density estimation. In this video, we reintroduce kernel density estimation. When using kernel density estimation, we are attempting to reveal the shape of a data set with a limited amount of information. In this video, we're going to take a look at investigating which movies in the dataset have the most ratings. We're going to be computing the KDE of a select group of movies using their rating. And then we're going to compute the KDE overlap of 2 movies. So I'm back in my virtual machine. I have the MovieLens dataset notebook up. I'm going to scroll to the top, and I'm going to introduce data.maybe. If you recall, this library is used in our KDE function. So I'm going to paste the KDE function. This is almost identical to what I used in the last section. The one addition is that I have added a normal line to the bottom of the function. With that, this is a normal kernel KDE with a standard deviation of 1. What I would like to do is I would like to run a query that tells me which movies in my data set have the most ratings. Not only that, I would like to get the title of those movies based on the items data set. Quick query DB, we're going to select data.item ID. So that's the ID number, and the items.title from data and items, where we want to make sure that the data item ID equals the items movie ID. Finally, we need to group by data.item ID to make sure our data items are grouped together. And we need to order by the count of the data.rating. And this is going to produce a lot of data, so we're going to limit our response to 10 records. So what you see printed out on the screen are 2 pieces of information per record. If you recall, the 2 pieces of information are the data.item ID and the title. The data listed will be in order what has the highest count in our data set based on the data item ID. So data ID 50 has the most entries in our data set, followed by 258, followed by 100, followed by 181. And those movies in order are Star Wars, Contact, Fargo, and Return of the Jedi. What I would like to do is to compute the KDE of the top movie in our data set, the one that has been reviewed the most often, Star Wars. So let's pull the data out of Star Wars. We'll call this Star Wars Raw, and we are going to just select the rating from data where the item ID is equal to 50. And that will represent Star Wars. Now let's convert the Star Wars Raw dataset into a list of doubles. I will just name this Star Wars. We'll be reading from the column in Star Wars Raw. If you recall, this is a single column dataset, but it's not easily accessible to access that one column. So we are going to grab the first row after a transpose. That appears to have worked. Let's look at the length of Star Wars. There are 583 ratings for Star Wars in this dataset. I would like to complete these 3 steps again with a different movie. And the one I picked out is Liar Liar. So let's go through these 3 steps again for Liar Liar. Liar Liar is 294. So I am going to rename Star Wars Raw to Liar Liar Law. 50 to 294. Good. Now, again, I am going to convert Liar Liar Raw into a list of doubles. Name this Liar Liar. And then finally, let's look at the length of Liar Liar. 485. So these are 2 different data sets, not only in the values represented by the list, but just the number of elements in that list. Next, we should compute the KDE. So we're going to compute the KDE of the Star Wars, followed by the KDE of the movie Liar Liar. We'll say just domain Star Wars. I'm going to name this SW for Star Wars, and then my KDE Star Wars. And then we'll pass in Star Wars to the KDE. And we'll do the same thing again for Liar Liar. So just domain Liar Liar, my KDE Liar Liar. LL is for Liar Liar, and then KDE Liar Liar. Next, I would like to display the data set. If you recall, the first data set is always in red, and the second data set is always in green, unless you override it. And for now, I choose not to override. So we'll just be plotting these 2 lines. Great. So as you can see, the red line represents Star Wars. It appears to be a well-received, well-reviewed movie. Notice that the curve produced by the kernel density estimator is slanted towards the high numbers, such as 4 and 5. In fact, you can make the case that it extends well past 5, on into 6, and even 8. Whereas the movie Liar Liar has a lagging curve behind Star Wars. Okay. Now here we see 2 kernel density estimators for 2 different movies representing 2 different data sets of different lengths. Now what I would like to do is see if I can draw a comparison between these 2 curves. How similar are these 2 curves? Well, you can clearly see that there's some distance between the 2. But what I would like to measure is this area. You see that point right there where the red and green line cross, and the red line extends down this way, and there's a green line that extends down this way. What I would like to do is to find the area formed by that triangular shape. We're going to call that the overlap, and I would like to find that area. IHaskell isn't going to let me work as long as this plots up, so I'm going to close the plot. Now, in order to find the area of that triangular portion in our 2 kernel density estimators, we first need to align the data sets. So let's look at the domain of the 2 data sets. So domain SW for Star Wars. It looks like it begins at -4 and extends almost to 10. And let's look at the domain for Liar Liar. It looks like it begins at -4, and recollection serves me, it extends almost to 10. These are identical lists. Now, the great thing about having domains that are identical And there's an easy explanation as to why these are identical. Both movies had at least one 5 and at least one 1. And because of that, the ranges are identical. The convenience of having identical ranges means that the KDEs also line up naturally. And in order to compute the overlap of these two KDEs, we simply look for any point in which one line overlaps another line, and then we take whichever one is on bottom. And then after we have accumulated all of the lengths of lines that are lower than another line, then we compute the sum of those. Here's what we're going to do. We're going to say sum map, and then I'm going to pass in two values. We'll call them Star Wars and liar liar. And then we'll say if liar liar is less than or equal to Star Wars, well then we want liar liar to be the representative line. Else we want the Star Wars to be the representative line. Okay. And then we're going to pass in our two data sets. I'm going to zip them. So my KDE Star Wars will be the first one, and then my KDE liar liar will be the second one. See here that we are adding up all of the lines. We are picking out whichever one exists on bottom, and we see that we have an overlap score of 0.65. Now you may be asking yourself, what does this demonstrate? What is 0.65? Well, this is known as a similarity score. A similarity score judges how similar two data sets are, whereas a difference score measures how different two sets are. Typically, with a similarity score, a score of 1 represents that two data sets are identical. And I can demonstrate this by taking my line, and I'm going to change the second data set over here to be Star Wars. We can see that we're passing in two Star Wars data sets to the rest of our line, and I get a line that is, with the forgiving rounding error of Haskell, these are identical lines. Now, if I were to pass in two completely unoverlapping lines, I should get a score of 0. So 1 means that we have lines which are perfectly similar, and 0 means which we have lines which are dissimilar in every respect. Now, while there's not a lot of application here, there are many applications in math and science in which comes the opportunity to look for the similarity between two data sets, and the data sets, for whatever reason, don't have the same number of elements. But with a little bit of work, you should be able to compute the KDEs of those two data sets, line them up along their domain, or in our case, conveniently, they're already lined up on the domain, and then simply sum up all of the values that are on bottom. And if you get a value 1, or at least close to 1, then you know these two data sets are going to be very similar. So here we have another data set that have 65% similarity. Now that does count as 65% similar, but I wouldn't go around saying that these are almost identical. It is time for our section summary. We converted a tab-separated and a pipe-separated file into SQLite 3. We performed a table join to combine ratings with movie genres, because we have a data set that involves multiple tables. Sometimes that requires a table join. We performed a table join followed by a group by in order to study how movie ratings change with age. And then we performed KDE on individual movies and compared the two directly, despite the fact that they have different values in each data set. So that is the benefit of the kernel density estimator. That concludes the course.